Good morning, everybody. It's 8:37 a.m. on the West Coast. That means it's time for Advent of Code, day 23 in Rust. But first, coffee. Whew, that is good. It's a good way to start the morning. All right, let us look at the problem. Look at all these stars. We got a nice little collection going on here, and we're coming right down to the end, which I am both sad and also kind of happy about. Sad because I enjoy doing these problems. Happy because I kind of don't want to be doing these problems anymore. At least just for a little while. Maybe for another 11 months or so. Let's take a look at day 23. Amphipods. First of all, we got to click on the link. What is an amphipod? They kind of look like shrimp. They are malacostracan crustaceans with no carapace and laterally compressed bodies. Neat. Are these like from the very deep sea? No. A lot of them live in fresh water. There are a lot of sub-orders. Is that what this classification is? Some of them are pretty gnarly looking. They have rarely been identified as feeding on humans. Oh. Good to know. I guess they're sea fleas. All right. Well, more power to you, amphipods. What do you got for me today? A group of amphipods notice your fancy submarine and flag you down. With such an impressive shell, one amphipod says, surely you can help us with a question that has stumped our best scientists. They go on to explain that a group of timid, stubborn amphipods live in a nearby burrow. 4 types of amphipods live there: amber, bronze, copper, and desert. They live in a burrow that consists of a hallway and 4 side rooms. The side rooms are initially full of amphipods, and the hallway is initially empty. They give you a diagram of the situation, your puzzle input, including locations of each amphipod, A, B, C, or D, each of which is occupying an otherwise open space, walls, and open space. All right, so we've got a little map here. Looks like we have multiple of each type of amphipod. The amphipods would like a method to organize every amphipod into side rooms so that each side room contains one type of amphipod, and the types are sorted A through D going left to right, like this. Amphipods can move up, down, left, or right so long as they are moving into an unoccupied open space. Each type of amphipod requires a different amount of energy to move one step. Amber amphipods require 1 energy per step, bronze amphipods require 10 energy, copper amphipods require 100, and desert ones require 1,000. The amphipods would like you to find a way to organize the amphipods that requires the least total energy. However, because they are timid and stubborn, the amphipods have some extra rules. Amphipods will never stop on the same space immediately outside any room. They can move into that space so long as they immediately continue moving. Specifically, this refers to the 4 open spaces in the hallway that are directly above the amphipod's starting position. Amphipods will never move from the hallway into a room unless that room is their destination room, and that room contains no amphipods which do not also have that room as their own destination. If an amphipod's starting room is not its destination room, it can stay in that room until it leaves the room. For example, an amber amphipod will not move from the hallway into the right 3 rooms, and will only move into the leftmost room if that room is empty, or if it only contains other amber amphipods. Once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. That is, once an amphipod starts moving, any other amphipods currently in the hallway are locked in place and will not move again until they can move fully into a room. In the above example, the amphipods can be organized using a minimum of 12,521 energy. One way to do this is shown below. This is the starting configuration. That looks like this. 1 bronze amphipod moves into the hallway, taking 4 steps and using 440 energy. The only copper amphipod not in its side room moves there. taking 4 steps and using 400 energy. A desert amphipod moves out of the way, taking 3 steps and using 3,000 energy. And then the bronze amphipod takes its place, taking 3 steps and using 30 energy. The leftmost bronze amphipod moves to its room using 40 energy. Both amphipods in the rightmost room move into the hallway using 2003 energy. Both desert amphipods move into the rightmost room using 7,000 energy. Finally, the last amber amphipod moves into its room using 8 energy. What is the least energy required to organize the amphipods? Here's our puzzle input. All right. This seems like a shortest path algorithm in heavy disguise. I'm not sure if I 100% understand all of the constraints here. And when I feel that way, I take a bite of a blueberry muffin. So cheers. And while I'm chewing here, I'm going to be kind of getting a feel for these rules. I'm going to try to sort of read them, digest them a bit. Okay, so I don't think this problem at a high level is too difficult, at least part one. It will be very annoying to code. Like I mentioned earlier, it's going to be kind of the shortest path algorithm. Now, the shortest path that we're talking about is not really moving a single amphipod from one location to another. Really what this is about is treating each sort of state of the map, so just every configuration of all 8 amphipods that is legal as a potential graph node. So what we will do is we will basically take our starting situation, and then for every amphipod that is capable of moving, we will create a new graph node for every possible move that can be made. So we'll iterate over all of the amphipods, find out if they can move. If they can move, we'll figure out where they can move. And then we'll just basically make a graph search based on that. Now, the annoying thing is finding out what the possible moves are from a particular state. And it's annoying for a variety of reasons. Oops. It's annoying because we have to basically create a kind of logical geography, a logical way to figure out where a particular amphipod can move. And that will involve doing a little mini search across the map saying, okay, well, like the space above me is open, so I could technically move there, but however, the space above, let's say this space right here, Amphipod B can't actually move there because it's not allowed to stop on the space immediately outside any rooms. That's not legal for me. So for every amphipod in any given state, we'll iterate over them and then find all the legal positions that they can assume, figure out the cost of those, and for each of those, we'll insert that as a node into our search algorithm, right? So we can start this one of two ways. One, we can just start by just copying and pasting our Dijkstra algorithm from a couple days ago, or I don't know how many days ago that was, but we had a solution before that used Dijkstra algorithm. We can just copy that over, or we can write a little program that, given a particular state of the map, iterate over all the amphipods and give us a list of valid subsequent positions. And then a way to hash that, right? And so maybe we will start with the latter, because that is, I think, potentially easier. Not easier. It's not easier. It's just new. Okay? So let's go ahead and give that a shot. I'm not sure how much time I want to spend parsing this input. I don't think it matters that much, although it could be potentially helpful for us if we want to be flexible. But you know what? I'm not going to bother too much with it. So how are we going to encode these positions, and how are we going to do our so-called collision detection, right? I think maybe we can hard code them because I don't think the map of this room changes. At least I hope it doesn't change. So we're not going to scan input for this problem. Let's actually get rid of the input file. Hopefully we don't regret this. And we are just going to start off with some starting positions, right? And maybe what we can do is just model some state for an amphipod. And they will have a type. I'm going to call this enum the word capital T type, and hopefully that's not a reserved keyword anywhere. And we have amber. Was it bronze? What were all these? Copper and desert. And why don't we go ahead and make this debug clone copy partial equal also hashable, because I think we're going to want to be able to hash these things because we're going to throw them into a hash set. Is that true? Really what we want to do is actually be able to sort these things. So we'll see. So an amphipod has a type. The amphipod also has a position, which is a, let's just call it an I32. It is a row and a column. And let's actually call it this, row and column. Okay? So we're gonna have some amphipods. Let start equal to a vector of amphipods. Would it be faster for me to type this or write a parser for this? I'm feeling kind of lazy. I think I'm just going to try to like type this out. The risk I run here is that I'm going to like make a typo somewhere. So I'm just going to encode this example because I think what we can do is like essentially work with this example and figure out like what we can work with the example and figure out whether we've written our stuff correctly or not. So we got a bronze one, and its position is the 0, 1, 2, the second row, if 0 indexed, and the 0, 1, 2, 3, third column. Second row, third column. And we're going to go from there. So we got a bronze one there. Right below it, we got a amber one. Its position is the third row, third column. Then we've got a copper one. Its position is the second row, fifth column. Below that, we have a desert one, whose position is the third row, fifth column. Over to the third column. Hey, Natty Bumpo, 23A, you solved manually. That's a clever way of doing it. I love it. I think this isn't the first Advent of Code problem that you can just solve by hand. I feel like a couple of years ago there was one where you had to like model an adventure game. You want to see what they did for 23B? Yeah, we'll see. I'm also looking forward to what fresh hell will break out in the second part of this problem. I'm going to write a problem for this because I'm going to write a program for this because I think it's fun. But I think I kind of agree with you that this is probably you could probably just try to do this in your head and figure out how to do it and get the answer. Probably the solution that you come up with might very well have a good chance of being the best possible one. Where was I, though? There's the desert one. I'm going to the third column. It's bronze. The third column is the second row down, the seventh column.
5 minutes later.
Okay, so what just happened is I literally ran out of disk space recording this stream on OBS, but I went ahead and deleted a bunch of stuff. Boy, video files, they really take up a lot of the hard drive space, don't they? Okay, so where was I? I was kind of rolling down the third column. We got a bronze one at 2.7. We have a copper one at that's gonna be 3.7, and we have a desert one at 2.9, and the last one here is a amber one at 3.9. Okay, does that look good? 2.3.3.3. 2.5.3.5, 2.7.3.7, 2.9.3.9, and that is it is bronze, amber, copper, desert, bronze, copper, desert, amber. Very nice. Okay, so we've got our positions encoded here, and then I think what we want to be able to do is to go from one of these states to a vector of subsequent states, right? So we're going to have a function that says get next states, and that is going to return a vector of amphipods. Let's go ahead and derive some traits for this amphipod here. Okay, so what we want to do is apply a bunch of our rules as we iterate over these guys, right? So we're going to have some result state that's going to be a vector of these other states. Oh god, I'm already just imagining how fiddly this is going to be. But that's okay. Let's not stress about it too much. So I'm going to get the index and the amphipod that we care about. I'm going to call it the apod. And it's going to equal, or this is not a let, this is a for. And we're going to iterate over our input states, which I'm going to take. I'm going to just call it source. And this is also a vector of amphipods. And we're going to iterate over this, and we're going to enumerate them as well. Okay, and so from here, what we're basically trying to do is we're trying to determine what are the possible places that this particular amphipod can go, right? So there are some degenerate states that we want to check. I guess we want to find all the possible locations that you can walk to from where you currently are, right? First of all, where are the valid stopping points? The valid stopping points are every location except for the spaces outside the hallways. Another thing is that do we need to kind of do a little bit of a flood fill or in order to figure out where you can move? And what's the best way of expressing that? So let's say you are Amphipod B, and you want to be able to move. I guess we can iterate over all of the locations and just ask ourselves, is this a valid place for you to go, right? And we may even want to be able to like read one of these things and actually get a map of positions. I also kind of wonder, while we're doing this, does the actual amphipod, do we care about this A and this A being different? Because according to the graph, it's always going to look the same. So maybe we can treat those two states as actually being the same. You can only perform two operations. One, move from room to one of the 7 hallway slots. Move from a hallway slot into a valid room. But you can also move into... I don't know why you'd want to do this, but it is possible to move to the first position in a room and not the second position in a room. Is that correct? Or is there a rule that says you have to go all the way into the room? So I think that the motion here is relatively simple. What we want, but where it gets a little bit complicated is just trying to figure out whether it's possible for you to move to a particular position or not, right? And that matters where you're going and where you're coming from, or that is affected by where you're going and where you're coming from. I'm starting to wonder if a better representation of our state is actually just a mapping of coordinates to... So right now we have like a vector of amphipods. We have a vector of amphipods and their positions, but I wonder if like a better way of representing this is a mapping of positions to an amphipod type. Valid room is the right room for your type of amphipod, and the room is... I don't know if that... I don't know if valid is quite the word I would choose, because you can be in a temporarily invalid state while you're trying to achieve a valid state, right? And I think that you like the shortest path may require an amphipod to temporarily step into a room, but only in the first position of the room, like where D is here, in order to get out of the way of another amphipod that's moving, right? That's a possibility that we could have. I like whether or not that's a smart move or not. I'm not sure, but I don't think the rules disallow that, right? And in order for us to prove whether or not that's a good or bad thing to do, we actually have to run the program and see. Or at least I have to run the program and see, because I don't think I have quite enough analytical capability to know whether or not that's a good idea. Natty Bumpo, did you do this? Did you do this program when the problem dropped? So I guess 12 hours ago. Nice. Um, well, hopefully this is entertaining for you and not killing you, because I might be kind of like treading water for a while as I kind of get the problem in my head. Amphipods will never move from the hallway into a room unless that room is their destination room and that room contains no amphipods, which also have the room as their own destination. Um, yes. That is. So if I were to just sketch out what we would do here, it's just like, um, am I in a room, or is a pod in a room? And if so, we're gonna follow a sequence of a set of logic here. Let's just say if a pod is in a room. Doing the problem manually really helped you understand the room problem. Yeah, totally. I can see that. And if you're in a room, let's say if a pod is in the hall. If you're in a hall, you can only move into a room, and you can only move into the destination room. Never move from the hallway into a room unless that room is their destination room and that room contains no amphipods. So what's interesting about this is this second clause that says that contains no amphipods which do not also have the room as their own destination. Which means that it is possible for an amphipod to move into a different room if they go directly from room to room, right? Like, can I move into my destination room? And then, should I move to the first location or second location? There's two possibilities here. Else the apod is in a room. And it's an unoccupied open space. So we have to respect the fact that we need to get out of the way for other amphipods. So if you're in a room, I think you can go from the second. You can basically move around within the room that you're in, right? So one possibility is move into other space in same room if available. Or move to hallway And then what we have to do, this is I think the tricky part, is like figuring out how to move into the hallway. For each valid hallway space, if there is an open path. The rooms are like a stack. Hey, patatas del papa. Does that mean potatoes of potatoes? What's a papa? It's one of the meanings, yes. Okay. Or potatoes of my father or something like that. Sorry if my knowledge of Romance languages is not very good. Natty Bumpo, the rooms are like a stack. That's actually an interesting analysis. I don't think I'm quite seeing what the significance of that is, but Papa is also how we call the Pope. Interesting. So does Pope kind of like if you're in like a different country that doesn't speak English and you say the Pope, do you kind of think of them as the father? Because it sounds like a synonym of the words that you would use for your dad. So I think I have naively mapped out all the rules here. So there are two overarching high-level conditions. An amphipod is either in the hall or it's in a room. And if you're in the hall, you have a specific set of rules. Really, if you're in the hall, you can only move into the destination room. You can either move to this first location in that room or the second location in that room if it's available. And this if here, if I can move into destination, if there's a path, you can't swap positions in the room. Maybe you could if the other position is the same type, but that's pointless. Yeah, I would say it's pointless, but it doesn't really cost us that much, right? Like I think we can model that as a possibility, but if it doesn't go anywhere, well, it does cost us, right? Because I think if we add that as a node into our search space, then we will have to waste time figuring out stuff for that possibility. I'm not super worried about that though. I don't think it like fundamentally changes the runtime of this, right? Why is it complaining about this? I'm getting distracted. Okay, it's just the return type. Okay. So what we want to be able to do is just basically ask these kinds of questions of our current state. So we want to just be able to model the state in a way that we can ask these questions, right? So our current representation of the state, it doesn't super behoove asking sort of these geographical type questions because we don't. When we're looking for paths, the naive way of doing this is we'd basically saying, okay, is my neighbor open? And you want to know what neighbors are available, and in order to do that using this sort of state representation, like a vector of these things, we'd have to like iterate over all of the amphipods continuously to figure that out. Which is why I think maybe potentially a mapping. The other thing we could do is just have like essentially a constant mapping between positions and their neighbors, which would make this a little bit easier to iterate over, right? And what would that particular data structure look like? I guess we can just call it a hash map of positions to amphipods. So I guess we could do something like this. Do you have a path from one position to the next? I don't want to have to solve like another minimum path algorithm for this. I almost kind of want to just like hard code all the paths. Let me take this map. Use the pathfinding crate again for this. Yeah, that's something that sounds pretty useful in this case. I am trying to do advent of code this year in an anti-crate way unless I need regular expressions. But otherwise, I'd be totally with you. Okay, I've just labeled all the positions using letters. This ABCD has nothing to do with the types of amphipods. And I don't really want to do every pairwise relationship here, right? Basically, I'm just trying to figure out if I want to go from position M to position A, what positions need to be open there? And I feel like there's no other option but to do pathfinding on this. Otherwise, I'd have to exhaustively enumerate all this stuff. It feels like the people that go really fast in advent code, they're probably using like I think everyone's using like Python, right? That's what a lot of the people who are fast use, and they've got access to some really nice libraries, NumPy, maybe something like the pathfinding crate in Rust as well. So you think the fast ones were all solved manually? That's totally possible. Yeah, probably there are people that are just really good at sort of like crunching these. But I think I'm also talking in general, right? Like people who are able to solve these problems like really, really quickly. If they're writing any code, I'm guessing that a lot of those folks are using Python, and they're using and the smart people like yourself are using crates that can help them out. Whereas the masochistic people like me are just trying to write everything naively. But that's part of like for me. That's I think one of my goals of doing this is just to be able to kind of like express basic algorithms. I'm not writing my own hash tables, right? So it's not completely artisanal code here. So I think maybe the thing is I don't have to do pathfinding because what you're just trying to do is like basically do a Manhattan style traversal from one coordinate to the next, right? So we can basically just iterate over, like if I'm trying to go from Surst and Dest, I can just iterate over each dimension as long as that position is available to me, right? So what I mean by that is I can go for DI in dest 0 minus in 1 to dest.0 minus source.0. That's the delta on that's the number of rows we want to traverse. And I don't know if this is going to be an equal sign here or not yet. Do I want to include this last thing? But I'll figure that out in a second. For dj in 1 to destination.1 minus source.1. There's really only going to be one option for us. So I think what we can say is like if it's not really even di. I think what it is like we're just iterating from what I want to do is actually, I'm going to say let di equals dest.0 minus source.0. Let dj equals dest.1 minus source.1. And I'm just assuming that source and destination are valid positions to land on. I'm not questioning that. All we're trying to do in hasPath is just negotiate the architecture of the hallway and also make sure that if there's someone in our way, then we account for that. So what we're really just trying to do is just add to I or add to j as long as like we're staying within the hallway boundaries. And we just need to figure out whether we're in a hallway or in a room, right? So our current position is where we are here. And if in room, I haven't written that function yet. Well, we actually have to figure out like which direction we're moving, right? Sorry, these are like basic geometric things, but I think even in these types of situations, it takes me a while to kind of grind the gears to figure out which directions we can go. So let's just try moving vertically, and then we'll try moving horizontally, right? We're going to move one step in the direction of DI. This just tells you if it's on the map or not, right? Whew, this is a tough one. Hey Dom, how you doing? Is this painful to watch? Is this painful to watch as I kind of like struggle with basic things? Nope. Thanks, Dom. I appreciate it. If you are interested, we can do this together. Let me know. So, if the source is equal to the destination, then we have a path. Boy, I never reach for recursion as the first option unless it's super, super obvious. And yet, in the last 3 problems, I think recursion has like really allowed me to simplify the problem pretty significantly. So let me talk through what this function is doing, and there's a big missing function that I still need to write here. This just has path. We have source and destination, and then we also have a map of occupied things, which I think we can safely ignore the source position, although it might technically be occupied in this. So if the source is equal to the destination, you have a path because you do nothing. Otherwise, we're going to get the total number of rows we need to traverse and the direction that we need to go. So it'll be assigned displacement here. Same thing for columns. If there is a non-zero delta in terms of the rows, we'll just say, well, the next step we're going to make in terms of rows is just one step in the direction that we want to go. And signum here just basically gives us a -1 or a +1, whether if di is positive or negative. And so the next space that we could potentially go to is just over there. But we need to make sure that it's actually an occupiable space on the map, which this function I will write. And we also need to make sure that no one's in there. And if we can move there, then the actual result is just has path. Whatever the answer is if we run this same algorithm, but occupying the next step down. And then we do the same thing on the x-axis. So this is for columns. The reason why we don't care whether we go rows or columns first is that you really only have one choice in this particular representation. If the map had open space, this would be a lot more complicated, and I would just probably have to write Dijkstra's algorithm again or something like that. Okay, so what I have to do right now is actually just enumerate all the occupiable spaces. And this isn't too bad. So we can just say if if the row is equal to 2, that means we're in the hallway. And we can even just say is hallway space. And all these functions I think we'll probably end up be calling again. We can just say that pos is equal to the row is equal to 2. And then converse and basically the opposite of is hallway space is a room space, assuming that this is a valid position. So if Well, I guess maybe let's be really clear about this. It's a hallway space if it's this pos dot one. What's the first column here? It is column index 1, and then we add 11 on top of that. Right, so this is column 12, so it'd be index 11. So it's 1 to 11. 1 is less than or equal to pos.1, and pos.1 is less than or equal to 11. That's a hallway spot, right? And then is room space. I32, I32. We're going to say that a room space is row index 2 or row index 3. And, boy, this is tedious. This column is either equal to 3, 5, 7, or 9. Not the most amazing code in the world, but I think because it's so naively written, I'm hoping that it will reduce the possibility that I'm making a silly mistake. Never a guarantee, but hopefully that's true. Okay, so I've written all these like kind of like super dumb helper functions. The goal is to build up this slightly more complicated function here, which is to just basically step us incrementally from the source to the destination given a set of occupied spaces. And then we need to actually digest what these occupied... we actually need to actually be able to create this hash set here. What happened to my indentations here? Did it just get formatted? It's a little bit too much service Rust format. Okay, so now we need to be able to just get the next states. So if you're in the hall, so if is hallway space apod dot pos, we are going to find a path to destination room. Rust format skip. Yeah, totally. We can do rough format skip. The only time I didn't want it was just because I had these comments indented. I guess like if I wanted to, I could just indent within the comment. I'm not sure how good that's going to be. One issue that I have with indenting comments is that usually indentations are even numbers of spaces, and yet I don't know how many languages use /space as your kind of like inline comment format. And I kind of refuse to use this style comment just because for some reason the activation energy of making like a multi-line comment like that is just like too high, so I never do it. Yeah. Okay. So the Rust book doesn't even mention. Oh, yeah, it doesn't even mention those like the C-style multi-line comments. Yeah, I feel like there's some languages that don't even have them, right? I don't think Go has them, right? It's just forward slashes. I never like writing code in Go, but for some reason, like more and more as I kind of like get to know the language more and more, at least it's not even that I get to know the language more and more because I hardly write Go code anymore. It's more like as I progress in my career, I kind of respect the design philosophy in Go more and more, which is that like basically like if a feature didn't seem 100% absolutely necessary to what they were trying to do, they just wouldn't include it, which is which at first I thought was just such a user hostile or developer hostile philosophy, but now I like it. I think it's probably because I've spent like probably 80% of my career writing and building stuff that I didn't need and shooting myself in the foot with it. So if we are in a hallway space, we want to path to the destination room. So we want the destination positions of a particular type. And this will be a vector of I32s. It's really just a possible. There's only like 2 possible options in here. And again, this is just like a map geography thing, so I'll put this next to our other map geography spaces. And this is also going to be super dumb. We're going to match on the type. If the type is amber, your possibilities are the space row 2, column 3, or row 3, column 3. If it's bronze, it is going to be row 2, not row 2. It's actually row 3 and row 4, right? This is a 5. This is a 5. What do you prefer, free function or method? You know, it really kind of depends. I think in a sort of like piece of code like this, where I'm probably only going to live with it for the next couple of hours. Well, maybe a couple of hours is optimistic, given that I've been super slow in the last couple of problems for advent of code. But in general, I do like the fact that I can write an implementation for this, right? And so, I don't know, just for the exercise, patatas del papa, why don't we just write this as a method, right? So we could do something like, I think what you're referring to is an impl type here, and we'll just do this sucker. Copy and paste it, and then we're going to be taking a self here, right? And I think this is what you were referring to, right? And why are you having an issue here? Why are you giving me problems? Oh, it's just because I didn't actually finish writing this. Copper desert. And I really want this thing to go away. Okay, yeah, so that's the... You know, I don't really know whether I prefer the method... I think in general, like, if you have a function that takes as its first argument some type of structure or enum value, if I was writing this code and it was going to be like part of a library, I would probably just make it a method. Just because I think the ergonomics are like a little bit better, but that's sort of an aesthetic thing. Even methods can be called in their free function form, right? So I think what you're saying is we could do something like type get destination positions, blah, right? Something like that. Yeah. Yeah, I think when I've written more sophisticated quote unquote Rust code, I've tended to prefer this style. So I guess maybe that's an answer to your question. Okay, if it's a where the hell was I going? If it's a hallway space, we want to get the destination. So for dest in apod type get destination positions. And in fact, I think the word get here is unnecessary. And in fact, this is actually a really long name, so I'm just going to call this the dest positions. For each one of those, if has path, source, dest, and occupied. So I think we need to actually figure out what is occupied right now. So let's make an occupied. Occupy Wall Street. Let's go over source.iter.map, or really, I think we're folding into a hash set. An accumulator, and we have a pause, and what this is going to be is accum.insert pause return accum. I'm not 100% sure if I love using fold here for this, but it does allow me to just declare occupied as non-mutable, which is nice. I prefer it when an API lets me do something like this, where inserting just returns the receiver of the method rather than some return value. Not that I'm saying that insert should work that way. I'm just saying that it would be nice if there was an insert version like that, so I could just use it in a fold gracefully. I keep adding parentheses in my if statements. I always hate it when I press enter by accident in the middle of a message. Yeah, I'm just, this is basically my life. Okay, so if there's a path, what we're doing is actually just creating a new state where this amphipod has moved to that destination. And it's going to be horrible writing this, right? So let a new state equals source.clone. God, there's going to be a better way to do this. New state dot remove I, and then new state dot push amphipod. Just type apod dot type, and its position is destination. So the path here is apod.pause, and then occupied I need to just pass as a reference here. Is that it? Oh, I am inserting amphipods. This is actually an amphipod. Let's just call it A, and this is a.pause. And you are complaining because it needs to be mutable. Fine. Fine. And then new state, of course, needs to be mutable. Now that we have new state, our result, we're pushing on new state. Okay, so if it's a hallway space, right? If you're in a hallway, you've stopped moving in a hallway, it will stay that spot until it can move into a room, okay? And you will never move from hallway into a room unless it's the destination room and that room contains no amphipods who do not also have that room as their destination. So actually, we need to, not only do we, this needs to have a path, we need to actually check to see, is my hallway, does my hallway have anybody else that is not on my team? And I'm just going to call this like, or not hallway, is room. Is friendly... it's not friendly room that I'm going for. Is room room has friendlies, and this is the type, and this is maybe, so we need different information, right? We need to actually know who is there, and it almost feels like I want to go hash map to type. And this, I think, technically could be method here. Gosh, this is a horrible mess of business logic. But bear with me here. Let's just call this state. Homeroom is friendly, and I'm going to call it friendly if it's empty or if it only has if it's occupied by amphipods of my own type, right? So first of all, we'll just get the homeroom positions. Either the state does not or let's actually do a match here. So let's do match on state dot get of the position, and if it's none, nobody's there, then it's true. And if it's some type, then this type has to equal self. So our home, is the current homeroom friendly? We're basically going to say, well, what are the positions of my homeroom? We're going to iterate over each one of those, and for all of them, based on this current state of the world, we need to make sure that nobody's in that position or that whoever's there has the same type as me. So this is the homeroom is friendly kind of thing. All right. So that means we actually have to construct this thing, and if we think about it, this hash map to type is like a better version of this hash set here that we were using before. So maybe occupied, maybe we can call this state instead, and this is a hash map. And what we're going to insert here is a.type. And then this instead is going to be a hash map to types, and these are both going to be just contains key. Now we are passing more information into hasPath than we technically need, but you know what, that's fine. And then there's a question of whether or not, should this state just be the thing that we're doing here? And it is tempting, right? For now, I'm just going to be accumulating this, but it might be better for us to just be passing something like this in and returning a new thing like this. We can make that conversion later if it's necessary. Okay, if it's a hallway space, it's like this. Otherwise, we return an empty result, right? Or we can continue here. I'm just going to continue here because I think I don't want an indentation down here. So Apod is in a hall space, is in a room space. Okay, so the options in a room space are a lot more sophisticated, or they're a lot more complicated. We can move to the other space in the same room if available. Natty Bumpo has said that this is actually kind of a pointless move. I'm going to add it in there anyways, just in case. Okay. So how do we know what the other space is? Well, it's going to be the same column, just a different row. So let row equal if pos.0 is equal to 3, then it's 4, otherwise it's 3. So one possibility here is to move into the other space in this room. It's probably pointless, but technically it's allowed by the rules, so we'll just cover it for now. So if it's not occupied, then we will push that on there. And we have to do this whole horrible thing. I think new state is always going to be the same up here. No, but it's going to be the same for each amphipod. So we rejiggered that because basically we want to be able to like start from a new state where the current amphipod has moved. We say base.clone, new state.push, amphipod whose type is apod.type and whose position is other space. So that we've covered this one. Move into an open hallway space if there's an open path. And then we can also move into another room. Which room can we go into if we're inside a room? Amphipods will never stop in the space immediately outside any room. One second. Never stop in the space immediately outside any room. That's fine. Amphipods will never move into the hallway into a room. And once you stop moving in the hallway, you can only move into your destination room. Okay. So we can move into any other space, basically. So we just need to... Basically, we can move into any other space as long as it's not occupied. So really, this is a pointless piece of code. What we can just do is enumerate all of the possible landing spots, given that you can't stop a turn outside a hallway. So I think what we want is just to enumerate all the possible spaces that you can land on. Oh boy. All occupiable spaces. And this probably should be a constant, but I'm not going to worry about that for now. Should I just type them all out? Might be faster than anything else I can do, right? I think it's 2, 2, right? 2, 2. All the way to 2, 11. I wish this was Excel suddenly, because I could just click and drag and it would automatically increment for me. $11, and then we're going to have, oops. What am I doing? This is actually 3, 3, 3, 3, 3, and 3. That's the first room space. Then we're going to have 3, 5, right? And then we're going to have 7 and 9. Now, this is technically not correct, right? Because not all of these hallway spaces are occupiable, right? Because basically the space directly outside each room is not occupiable. So that means that well, first of all, I need to actually add one here. Just 2, 1. 2, 1. So this one's not occupiable. This one's not occupiable. This one's not occupiable, and this one's not occupiable, right? So now to get this right, we have 7 hallway spaces that are occupiable according to Nathaniel Bumpo back in the chat. 1, 2, 3, 4, 5, 6, 7, and then we have 2 room spaces. Am I missing I'm missing the 9s? No, I got the 9s in there. I'm missing the 5s. It's column 5. Okay. So this should be 8 lines of code here. VS Code doesn't tell me how many rows I've selected because I'm just not cool enough, but that's okay. 58 minus 51 is 7 plus 1 is 8. Okay. So then we got them all in there, but this is a typo. It's always row 3 and then row 4. Okay, so those are all the occupiable spaces. So what we're going to do here instead is if you're inside a room space, you can basically move into any other occupiable space as long as there is a path getting you there. So for P in all occupiable spaces, if there's not has path from apod.position to P, let's actually call this dest here. We're just going to continue. There's no occupied. Oh, it's just because it's state. If there's not a path, within, fine. We also want to skip our current position, right? So if dest is equal to pause, apod.pause, or there's no path to where we want to go, we'll continue. Otherwise, we'll do this stuff. And what's nice about that is I don't think we need this get other room space anymore, which is a gross function as it was. And all this stuff is gone. And the result here is a vec amphipod. What am I doing here? Where is this type being set? Let's actually just set the type here. And this will tell me where I've introduced a typo. Actually, I think we had that code correctly to begin with. Oh man. Okay, so this is the basis for our possible moves. So let's just call it on our current state and see what we get. I need to account for this rule, don't I? So if I need to actually use this is homeroom friendly. Amphipods will never move from the hallway into a room unless that room is their destination and that room contains no amphipods which do not also have that room as their destination. Did I encode that into the rule space already? So if we're in a hallway space, we're going to go to all the homeroom positions. If there's a path there, I haven't actually accounted for that. So we can't move into any of these if the homeroom positions are occupied by if we're in a hallway space, we're not going to do any of this stuff unless if apod.type.homeroom is friendly. It's not friendly. There are hostiles in the homeroom. We're done. We can't do anything. The only thing you can do in a hallway space is move to a different hall. Oh, I guess we can move to a different hallway. No, we can't move to a different hallway space because of this rule here. We can only move into our friendly room, our own room, and only if that room is friendly right now. Okay. Oh boy, that's a lot of stuff. So we're just going to run this on the initial state, and unpromisingly, we basically get nothing. So I'm going to actually debug here. In order to do that, I need to actually have a debugging launch config. I think just LLDB will work. And let's go ahead and launch this bad boy. Okay, so stepping in, our state, does that look like our initial state? Bronze on 2.7, just doing some random sampling here. Amber on 3.9. Okay, so far so good. Now we're stepping into the for loop. We're going to get our first Amphipod. It's not a hallway space, it's a room space. So, okay, so this is already a problem, right? Is hallway space apod.position. The position is 2.3. So this is registering as a hallway space. So I think our is hallway space function is not correct. If the row is 2, so I think I got this wrong. I think what it is I've been calling the second row the third row because I'm off by 1. All the time I'm off by 1. So 2.3, let's take a look at the map again. This is the 0th row, the first row, the second row. Okay, so the hallway space is actually 2. Or rather, the hallway space is actually 1. So I need to rejigger all of my coordinates. This is row 2. This is row 3. This is row 2, row 3, row 2, row 3, row 2, row 3. All occupiable spaces. These are the hallway spaces. These are the room spaces. The hallway is actually row 1. So that means all of these are 1 as well. And then this is 2 and 3 now. Row 2 and row 3 are room spaces. It is a hallway space if we are in row 1. It is a room space if we're in row 2 or row 3. Okay, that's correct. Sure check. Is this part 1? It is part 1. Yes. Okay, so that should solve a lot of our bugs. But it didn't, so we'll just continue debugging. This is all totally expected because I wrote a lot of code without running anything. Okay, so it's not a hallway space, which is great. Our destination is all the occupiable spaces. What's the destination right now? And who are we actually considering? Which amphipod are we looking at right now? We're talking about the one in position 2-3, the bronze one. No problem, Shurshak. It's good to see you. 0, 1, 2, 3. Okay, so we're talking about this one right here. So this should actually have a lot of possibilities for moving. So it's great that we randomly landed on this particular one to sort of like sort through. And in fact, maybe we want to actually adjust our starting state to get rid of all of these, just to see, just to make sure that we're doing this correctly. Okay, so the destination that we're currently looking at is 1, 1, and so we should be able to go to 1, 1 from 2, 3. So apod.pos is 2, 3, destination is 1, 1. They do not equal each other. So we just want to make sure that there's a path there. So it looks like our bug is in this has path function. It's giving me assembly language when I actually go into has path, so maybe I will actually set a breakpoint in has path just to make sure that we get in there. Okay, so this is great. Our starting position is 2, 3. Our destination is 1, 1. And just look at the map again, just to make sure I haven't screwed up the math. This is row 0, 1, 2. Yes, that's the second row in a 0 index space. And then it's 0, 1, 2, 3. Yeah, so it's 2, 3, and then we're going to 1, 1, this corner spot right there. Source and destination are not equal to each other. The delta on in terms of rows is -1. If it's greater than 0, this is actually what, let's see what the issue is. It should be not equal to 0. Hi, Shishak. What's the algorithm? Well, okay, the algorithm, I haven't even gotten to the true algorithm part. I'm just actually implementing all the nasty business logic. And the business logic I just implemented is just given a vector of amphipod positions, which I'm just calling a particular state. That's what this is. I didn't write a parser for this because I thought it would just be really, really mistake prone. I just encoded the input into a vector like this manually. I just want to be able to call a function on such a vector and return all possible future states. Or just give me all of the moves for all of the amphipods that can move, right? And then the algorithm is just going to be basically each one of these things. If we just take it as a blob of state, is going to be a graph node in Dijkstra's algorithm, because we can compute the cost of one of these steps, I think, relatively easily. Okay. So let's try and run this again, because I think this not equals 0 gets us a little bit further. Okay, so we got a bunch of output here, and this is going to be a little bit tricky to kind of sort through because there's a lot of stuff here. Maybe what I really care about is what the move actually is. So maybe it's just a delta of the amphipod index and its destination. Let's do it that way. So let's call this a U size and its new position. It's like chess. One of the first things you did was write a display debug for your state. Yeah, that's a good call. And I think probably one thing that would be nice in terms of displaying this is to just draw the map, right? Instead, what this is going to do is, what I'm going to do is just call like get next moves, and this is going to give me a slightly more compressed version of what I'm interested in. This is like a chess move, right? So like given the state of a chessboard, what are all the moves that are possible right now? Shurshak says, I heard many people solve part 1 using manually, which is actually what Nathaniel Bumpo, if you scroll up in chat, they were saying that they did that. Potatoes del Papa, never use a debug or println and debug have always been your best friend. Totally. I actually just installed the LDB plugin for VS Code yesterday for yesterday's problem. I've gone back and forth in my career between just using printf debugging versus doing interactive debugging. And I think if you can do the interactive debugging, it's really, really great. But you should know how to do both, I think. In this case, the code is complicated enough, and I have a poor enough understanding of it that it's actually helpful to me to be able to kind of watch the code run. In previous years, I feel like there wasn't even a great LLDB VS Code plugin, or I just didn't know about it, so I was like literally using the command line interactive debugger for LLDB. And there are some people who are just like straight up wizards with command line debugging. You can script those debuggers, that you can do all kinds of crazy stuff, and it's a level of programming that I've yet to achieve. I actually like this change a lot that I'm doing here. It's like, give me all the chess moves from a current state. Might be a little bit easier to read as well. It's so cool that the Rust compiler or the Rust analyzer has enough knowledge in ergonomics. They can basically do this kind of like, oh, you had a typo in your identifier. Maybe you mean this other thing. It seems like that would be difficult to include without making the tool super complicated. Okay, so here are all my moves. Can I copy that? I don't think that worked, but let's see. Yeah, it didn't work. I guess PB copy just doesn't work in the VS Code terminal. I don't know why that's the case. Maybe it doesn't have access to the clipboard. All right, so here are all my possible moves. Unfortunately, though, I've got like position 0 here, or I guess it's like item 0, which is this guy. And just manually, what are the moves that they can do? They can go to like, essentially they can just make hallway moves, right? They can make a hallway move to here, and they can move to every single hallway spot except for 3, 5, 7, and 9. Right? So that's 1, 1, 1, 2, there's no 3, 1, 4, there's no 5, 1, 6, there's no 7, 1, 8, there's no 9, 1, 10, and 1, 11. And then the same thing for index 2, which is this guy, and also index 4, which is this guy, and also index 6, which is this guy. So that's what we'd be expecting. 2, 1, 1, 1, 2, there's no 3, 1, 4, there's no 5, 1, 6, there's no 7, 1, 8, there's no 9, 1, 10, 1, 11, and then we're going to index 4, same deal. Then we're going to index 6, same deal. So at least for this initial step, we have gotten correct moves, right? So let's try something that's a little bit more interesting. Maybe we can start with a state where the bronze one has actually moved to the first position. And Natty Bumpo, I'm like on the verge of writing something that will visualize my state, because this is annoying. Okay, so here are the next moves, assuming that the bronze guy has moved to this first position here. So he can only move to hallway spots. Right. But this does open the possibility for the amber, amphipod to also move outside of here. So let's actually look at like what. Wait, why? So this is interesting. This should allow Oh, wait. The 0th amphipod, which is the bronze one, can't move anywhere because it's in the hallway and it can only move into the second column, but the second column is fully occupied, or rather the second occupiable room is fully occupied, right? I just realized something. The homeroom positions. Okay, I did do the homeroom positions. I was like, did I write this code? And it's been long enough already that I just completely forgot that I did. One of the things I'm secretly sort of like tacitly, it's not tacit anymore, I'm saying it out loud, but one of the things I'm kind of like slightly worried about is I've mixed X and Y in rows and columns in all of these coordinates. Easy thing to do. Okay, so the amber amphipod, which is the one over here, now has a set of moves. It can move to 1, 2. It can move to basically all the hallway positions except 1, 1 because the bronze one is occupying it right now. So far, so good. And it can also move to the other position in the room, which is what we wanted. Is there any other move that is interesting in this situation? I don't think there is, because none of these other guys that are here can move into this open space that was vacated here. So I think maybe the thing that I'm interested in is actually moving this amphipod C into the corner, which will allow B. Well, it won't allow B to move into this second column because D is also in there. So let's actually try that. So we're going to put this guy back to where he was originally. And now we're going to move this one to 1, 1. In fact, let me just comment this out because otherwise I'm going to forget what the original value was. So all I'm interested in is what this first guy can do. This first guy can move to all the hallway spots that are occupiable. And he is not allowed to move into this second column because D is there. Now let's move D out of the way, that guy. So same thing here. We're going to comment this out, and we're going to move him to, let's just say 1, 2. That's the other hallway spot. We're going to run this. And now our initial bronze amphipod should be able to move to all the occupiable hallway spots, but it should also be able to move to the 2 spots in this room. 0, 1, 4. Okay, these are all the hallway spots. And it doesn't look like he can move to row 2 anywhere. Why is that? So this is a bug, right? Like in this situation, this first amphipod here should be able to move into this room right here. And so I'm interested in finding out why he is not moving in there. All right, so let's go ahead and do some debugging. Okay, so we should be starting with the bronze one that is at 2, 3. We should be going through all occupiable spaces. And what we're interested in is the space 2, 5 and the space 3, 5. And that's not gonna occur to us for a little while. So let's watch destination here. Let's just scoot forward. What just happened here? Here we go. Okay. So 1, 2. 1, 4, 1, 6, 1, 8, 1, 10, 1, 11, 2, 3, 3, 3, 2, 5 is the one that we care about here. So now we're going to set a breakpoint in hasPath. So we're in 2, 3. That's this one. And we want to go to 2, 5. That's that one. Oh, didn't mean to type there. So if we're going forward, our path, we're not going anywhere. DI. Oh. Okay, I see what's going on here. In order for us to make this move, we actually have to move up and then down. That's super annoying. So this hasPath, unfortunately, is too naive right now, because in order to go from room to room, you need to go up and then down. You chose never to model room-to-room moves, since technically you stop off in a hallway. Yes, that is absolutely true. I don't know if that's actually technically true, right? Because let's take a look at the rules specifically. So I believe, like, Natty Bumpo, I believe you that, like, you might be able to find an optimal solution without modeling the scenario. But if you don't model room-to-room moves, you're actually eliminating one possibility in the search space, which is that if you're currently in a room, you are allowed to move to another room that is either not the one that you can go into. You can go into a room that's not your home room. You can also go into a room that's occupied by a different, by essentially a non-friendly amphipod, right? No, you aren't allowed to do that. Okay, well, if you can quote me the rule that prevents you from doing that, then I will believe you. It just says amphipods will never move from the hallway into a room. Okay, I see. So it depends on how you read this rule. And so, Natty Bumpo, if I'm reading this rule the way that you're expressing, is that you always have to go through the hallway into a room, right? And so if you think about it that way, then this rule of, like, you're just basically not allowed to enter a room if it's not your own room, and it's so what's confusing to me is that there's this second clause here. You're not allowed to move into a room unless that room is the destination room, and that room contains no amphipods which do not also have that room as their own destination. So I think if we're basically saying you as an amphipod, when you're making a move, you can never go in. You can never enter a room unless it's your home room. Then the only way that this second clause is possible is if an amphipod was in that room because of the initial state, right? I guess when I read this, I was like saying, oh, there must be a way for an amphipod to move into a room that's not their home room. And the way that I read this is that you can't move from the hallway into a room, but I was thinking you could move from room to room if you consider that like one step. So it's a little bit ambiguous to me the way that this is worded. The second clause means the room is either empty or only contains the right amphipod. Yeah, I think that's correct. But the question is, how can it contain the wrong amphipod, right? That's the question I'm asking. Because if you're only allowed to move, if an amphipod is only ever allowed to enter a room if it's their home room, then how could this second situation have happened? It's because of the initial state, right? So I think you and I are saying the same thing, right? So I think the only source of confusion for me is like, does if you initially start from a room and you move into another room, does that count as you moving through the hallway as well? Right? Like it does is a move from the hallway mean that you had stopped in the hallway and then moved into the room, or is it like, well, because you're in a room, you have to go through the hallway? And I think, Natty Bumpo, you're saying it's the second. And if that's the case, then we don't even have to model the kind of room to room motion, right? So I think what you're saying is that rather than if you're in a room space, we should just get not all occupiable spaces. We should get all hallway spaces. There is technically the kind of like go to the other space in the room, but I think you had said earlier that that's like a pointless thing to do. So let's try that. I think it'll simplify what we're trying to do here. So I guess we just want all hallway spaces. And that's just this. We're not calling one function. Okay, so we're not going to be able to get too much confirmation here. Let's move this amphipod into position 2, 4. So we're moving. So our state was this initial state, but we moved this C and this D over into the corner there, and now we've moved B over to this spot here. And so he should be able to move into either of these two spaces. Zero, 1, 4. So he's moving to the other hallway spaces. Okay, so I'm still not seeing the thing that I'm interested in. So let's go ahead and let's do a break right here, and we'll debug again. Oh, I see what I did. This should be 1. Helps to have my rows straight in my head. So 0, 2, 5, great. 0, 3, 5. Okay, perfect. That's exactly what I was looking for. Okay, I think I have enough intuition here. If I was a smarter person, I would probably just like write debug prints for all of these states. But I'm gonna go ahead and try to like plug this into Dijkstra's algorithm and then see where it'll take us. So I'm gonna restore my initial state here. Starting to wish I'd written a parser, but it's the price I pay for being lazy. So that's our start. And then I'm going to maybe go back in time and borrow a Dijkstra implementation. Or we can painfully just watch me try to think of it again. We'll not do that. We won't do that. So how many days ago was the other graph search? It's been a long time. So is it bin heap? That was day 20. So for us to do this, we need a notion of a stopping point or graph node. So what we want is going to be a state, which currently we're calling a vector of amphipods. And the cost, which is an I32. And then we need to implement some traits for this, just so these things can be sorted against each other. Other dot, so this is all cost. We need to import all of this stuff. And now we also need to implement, we need to derive some traits. So let's go ahead and derive debug, clone, what is it, equal, partial equal. Sweet. So that gives us our cost. And then two nodes at the same cost are going to be, we're just going to consider them to be basically equivalent to each other in terms of our ordering. So now we want to find the shortest path. Oh, use Dijkstra on day 15. Did I use Dijkstra on day 15? I don't even remember what day 15 was. You have a good memory for these things. Whereas I can't remember what I did yesterday. What was day 15 again? I'll go to the more complicated one. Part B. Oh, I did Dijkstra here too, it looks like. Yeah. I don't even remember doing Dijkstra twice. It's so funny. This actually rings a bell to me because, like, I remember doing a comparison function that basically compared against a cost and then something else. Is it the cave one? Yeah, very well could be. Okay, let's set up Dijkstra then. So we're gonna have our binary heap with a node on it. We're going to import that. And we are going to seed that with the initial state. Push. I wish Rust's data structure would just have consistent terminology of how you add something into a data structure. Is push the normal terminology for a heap? I guess it is kind of push and pop, right? Basic, creation, internal. They call it insertion. Not that Wikipedia is like the source of canonical language for computer science. I just feel like push and pop are like strictly stack terminology, right? And even then, I wouldn't hate it if we just called it like insert and remove. But instead, we're kind of stuck with these like weird semantics and weird terms. But I'm kind of weird, and I even don't like the term vector for these types of data structures. I feel like there are other languages that call this array list or something like that, and I'm actually fine with that terminology. Vector, to me, just makes me think of a math vector, and it's annoying. especially if you do game programming, which is what this stream is normally about, and then you get confused between like, am I talking about a growable list of things, or am I talking about a multi-dimensional value that I can do math on? All right, so we're going to push on the initial state, which is the start, and then we need to make some progress. Do I need to clone here? Can I just move it? This is a vec of Amphipods. I need to make a note out of this. The state is the start, and the cost is 0. And I always have to remember how to do Dijkstra's algorithm every time I write it, because I basically have to do it like 5 times in a row before it sticks in my memory. But as soon as I start doing it, I kind of start to get the feel for it. And here we go. We are going to start popping out this thing. So Java only chose array list because they already implemented the same data structure named vector, and they realized that there was fundamental problems with the design. Yeah, so probably Java was following C++, right? Because the C++ standard library had vector, and I think they might not have been the first people to call that sort of thing a vector. But I don't know. Like, in mathematics, if you're doing linear algebra, is it common to kind of, like, have something called a vector and then add another dimension to it? It's weird, right? I guess they're trying to use vector in the most simple form, where it's, like, the opposite of scalar. Still, not a huge fan of that terminology. So while let node equals pq dot pop, we need actually some sort of way of knowing if we've gotten to the end, right? So what does that mean? So fn is finished for a given state. And this one, we can just use whatever state representation we have, which is the vector of Amphipods. Returns a Boolean. And what I'm going to do is for each a in state.iter, didn't I have a thing that gives you your homeroom? Yes, homeroom positions. Let's do this. State.iter.all. And we've got an amphipod. And the amphipod homeroom positions dot contains. Do I need to iterate over these? I do. This is a vector, right? There must be like, is it index of? Oh, it's got contains. Does it contain the amphipod's position? And this will tell us whether or not we're done, right? We're going to say for all of our amphipods, let's get the homeroom positions for that amphipod, and does it contain the amphipod's position? Now, this is assuming that the state is well formed. It's assuming that the amphipods aren't standing on top of each other. But I think this will do it for us, right? So what we're doing here is trying to get our final answer, which is the cost, right? That's basically what we're going for. What is the least energy required? And so what we're going to say is if is finished node.state, reference to that, then we print victoriously our cost to get here, and we are done, right? And then that means that it should be unreachable outside of here, right? Okay, what are you complaining about? Homeroom is friendly, we never call. Oh, right, we just have a bunch of functions we never call. And this linter here, this never called linter, is almost too powerful. It's basically saying you never even transitively call any of these functions. Okay, so going back to our algorithm here, we just want to get all of the next states. Um, that is our current state. So we've got next moves. Okay, so the next thing we need to do is make sure that the equivalent state doesn't have a lower cost already. Right, and I think that's what this is. So I need to basically have a mapping between a state and its lowest possible cost. And that was the thing that I jumped over here. Okay, so here's a tricky thing, is that my state is a vector, and can I hash a vector? I don't know if I can. Yes, you can hash a vector, so that's cool. This is start. Did I move start already? Is that why it's complaining? I guess I just have to clone here, right? Or I have to clone here. And then what we have to do is we actually have to take this vector of next moves, and we actually have to apply it to the state. So I removed that code before, but I actually have to apply it to the state. Okay, so we're going to iterate over these. For move in get next moves. Now we need to create a new state. Oh god, I forget that move is a keyword in Rust. For M, let's just call it M. So what we're going to do is we're going to say let next state equals node.state.clone. We are going to remove I, then we're going to add, oh, and then ordering matters because the vector cares about ordering, whereas otherwise we don't care. So we actually need to sort these. Either that or I could just overwrite I. Yeah, I'll just overwrite I, and that way the sort of the ordering will be preserved. So I is the position. It's basically the index of the amphipod that we moved. We're just overwrite it. And again, this is actually going to double, or potentially, it's going to multiply the number of states that we care about unnecessarily. So there's going to be some redundant states in here, because this is actually treating one amphipod as different to another amphipod. Like, it'll treat amphipod A, the first amber amphipod, as different than the second amber amphipod, whereas I don't know if that distinction really matters for this search. I don't know if it's going to kill us, though. So the next state for this particular amphipod is just updating its position. So what it is this new amphipod whose type is equal to the previous amphipod's type. Not state, node.state. And their position is equal to m.1. In fact, maybe I should just call this like and then I can avoid some of this stuff. Oh, but I do need the index because that's what I'm overwriting. So never mind. Or this is actually, yeah, I can't just rename it like this. So this is ID next position. ID node.state ID.type and next position. Okay, so now what we want to do is we want to make sure that we want to know what the cost of this is going to be, right? And so we need to actually return the cost of we need to actually know how expensive this is going to be. So either we could write the function to do that, but it kind of feels that has path. Maybe we should be the one to calculate that because we are kind of inching towards it. Right, so it's more like path cost. This will return an option for an I32, which is the cost. Right? And in order for us to know this, we need to know what type is moving, right? Maybe what we can do, though, is just return the number of steps that it took. Is it just Manhattan distance? It is just Manhattan distance, right? Because we're not moving backwards. So maybe what we can do is figure it out. I'm going to just throw this into another function. Fn get cost, source, I32, dest, I32, type. And so what we're going to do here is let step cost equals match on type. And actually, maybe the step cost is something we can throw in the enum. Per Patatas del Papa's preference or suggestion, let's get step cost of self, which is an I32. Go to match on self, and then just do a little table here. I'm going to copy the table up here. And I don't even remember. I think it was orders of magnitude, right? I think amber was the fastest or cheapest. Amber is 1, bronze is 10, copper is 100, desert is 1,000. Bananas. $1,000. Okay, so now, maybe in this case, I'll just make a Manhattan distance function. And that is just dest 0 minus source 0 dot absolute value plus dest 1 minus source 1 dot absolute value. Almost makes me wish I was using a vector library. So let cost is equal to the Manhattan distance of node dot state ID dot position. That's the source. The destination is the next pause. And we're going to multiply that by node. I'm actually going to get that node. Let prev apod equals this. It's prev apod. Prev apod dot type dot step cost. So this is the cost of this particular move that we're making here. And what we need to do is to look up in our lowest costs whether or not we should even make this move, right? If let sum, what is the actual structure that I used here? Yeah. Lowest cost of lowest cost dot get. Of next state. And it is no dot cost plus. Expected U32s. I somewhere introduced an I32 where I. Let me just make this an I32. It doesn't really matter. I don't think like unsignedness, sign safety here is a big deal. Okay, so we've calculated our next state here and the cost that's involved. And if we have already attempted to process this state at a lower cost, then we should skip this. Otherwise, we need to throw this sucker onto the priority queue. Right? So the algorithm for Dijkstra's, I think I copied this from the Rust binary heap documentation, and they actually did this lowest cost check twice. Once when you pop off the list, and then once when you're actually handling each next step. And so I'm doing the second of those. If I wanted to copy what I was doing before, I'd actually add this up here as well. And I'm not sure if I remember why that step was necessary. There must be some edge case where you could get to this point and add on an attempt to process these. I don't know if this is 100% necessary. This optimization, to me, seems redundant to this one, right? Because if you're in a particular state that matches one before, but you already had a lower cost, the only thing you're saving is just like calling this and then getting rejected on every single iteration for this one. Which, you know, is not nothing, but it's not like huge. You're not creating like a you're not really creating a multiplying effect because it's not going to branch out past this point. So I think maybe for the sake of simplicity, I might try to omit this check. And if we're running into logic problems, maybe I'll have to add this back in, but it doesn't seem like this one's 100% necessary. Okay, so where we are at is we actually, now that we've sort of like checked the cost of this thing, if we actually have found a lower cost way of getting to that state, then we should push it onto our priority queue, right? So what we're going to push onto the priority queue is a new node whose state is next state, and the cost is just the cost that we calculated above. And that is Dijkstra's algorithm. Voila. Okay, it's taking a while. It's taking a while. It's taking a while. Hopefully we're not infinite looping. That's always a possibility when doing this. This feels like it's long enough that like we probably got an infinite loop, which means I'm missing some check somewhere. And the first check I'm going to add is the one that I explicitly said I was omitting. Yeah, so we immediately hit this unreachable, which makes me think that potentially this is finished is not working correctly. But this one's simple, right? Doesn't look like we need this all occupied spaces function anymore. I'm going to go ahead and just get rid of this so the warning doesn't distract me. Okay. So this actually gives me the optimal path right here. Right? So there's lots of different points of failure. The one could be that I encoded the initial state incorrectly. One could be that the structure of my algorithm here is not correct because of some subtle thing. One could be that this is finished criteria is wrong. And then potentially I've gotten the next move calculation wrong. Right. This is probably the one that's most fertile for bugs, because under get next moves, I spent the first hour and a half trying to just figure this out. Right. And so the longer you spend on code, the more code there is, and the more code there is, the more likely that there's going to be a bug. So what's the first step of debugging? Let's just make sure that we're getting this is kind of functioning the way that we expect it to, right? So let's go ahead and fire this up. Okay, so we're not finished. Oh, why did we immediately skip this? Oh, because we added the lowest cost already. So I don't think we want to insert this yet. But we want to make sure we don't try to reprocess the initial state, right? Which is entirely possible. And yet, I think this less than or equal to is pretty important, right? If I get rid of this, then it'll progress. Actually, I don't think it rebuilt, so let me just run this again. So we're in step. Okay, now we're going into the first one. We are missing that less than or equal to, which I'm a little bit worried about. I think adding that equal sign there actually solved a bug in this a week ago when I was working on day 15. I'm just going to let this run and see where it takes us. I think we're infinite looping again. So one other thing I'm curious about is are we getting into states? Are we getting into states that don't get us anywhere? Or that somehow hashing this is not giving us the correct answer? So like Rust hash vector, what is actually going on here? This is the most obnoxious thing on the internet. I'm just trying to make sure that when we hash over a vector, we're basically just doing a value-based hashing, because that's what we want. It has to be. It has to be. This is ultimately just an array of bytes, right? There's no references in here or anything like that. And an array of bytes should be deterministically hashable. Okay, I'm going to talk out loud just to make sure that I have not made a silly mistake in Dijkstra's algorithm. So we have our queue, or our priority queue of next moves that we're going to make, or rather states that we're going to start from in order to guess next moves from. We have our initial state, which has a cost of 0. It didn't cost us anything to get there. And then we're also basically mapping our states to costs. This map here just gives us the lowest cost that it took to get to a particular state. And this is so we don't infinitely retry stuff. All right, so we're going to take a particular node, which is just a state plus cost, off the priority queue. If it represents something that's finished, that means that this is the first time we've got to the finished state at the lowest cost we possibly could have gotten to, so which means we're done. So we print it out and return. Otherwise, we check to see if this state that we've gotten to has a lower cost. Oh, you know what I'm not doing is I don't think I'm adding to the lowest cost list ever, right? I'm not pushing into that. So that's what I'm missing. It's this sucker here. This is the problem with copying and pasting and not thinking. Since we're doing our cost processing here, I'm actually going to stick this here. And I'll just clone. Why don't we just clone everywhere? This clone technically isn't necessary, but we're going to clone everywhere. So we are getting to unreachable code. So let's just debug again. If there is a lowest cost and it's less than, okay, yeah, okay. So we'll carry on with this. And again, I'm not convinced this is necessary. What if I? Well, let's actually modify one thing at a time. Next state. Our move is to move this guy to this corner here. The cost of that is 30. That's right, because he's a bronze. Each step costs 10. And it is 1, 2, 3 steps, so that's 30. So the cost is being calculated correctly. So we insert next state there. And next state, our bronze guy is at 1, 1, and everything else should be the same as before. And then we're moving ahead. Next state is to move the bronze guy to this spot. All right, so this is going to go on. So I think the only possibility here is that, like, we are just not materializing moves that will ever get us to the right spot. So one thing we can do, maybe to be super laborious about this, is we can maybe try to walk through these different states and see if get next moves is going to give us the move that we're looking for. And in order for me to do that, I'm going to actually want to parse this thing, which I was just totally trying to avoid because it's annoying. But let's just go ahead and do it. It's not that big a deal. Parse the string, and it's going to give us a vector of amphipod positions. And then what we're going to do is we're going to split into lines. We're going to enumerate them. This is going to be the ith line and the string for the line. We are going to have a vector, which is our result. And then for each character, if we're going to match on the character, if it's an A, then our type, we're just going to push an amphipod whose type is amphipod amber, rather type amber, and our position is I and J. It's a little bit of repetition here. I'm not too busted up about it. It's easy to read. Otherwise, we do nothing. And then we return the result. This is a U size. I can make all my positions U sizes. Might make the subtraction a little bit weird. So let's actually just do this as I32. Okay, so that's our parse. That was way faster than I thought it was going to be. So how do I do multi-line input in Rust? Multi-line string. I believe there is some fun delimiter. Is it R hash? I think it's R any value, right? our quote, and then we can do this. Why am I not allowed to select this? Wow. I think that's one map. That was a really difficult thing to paste. And I think we can trim off of this, right? So maybe we actually want to do a trim here. source.trim.lines. But we don't want to trim the subsequent lines like this, which I don't think we're worrying about. This is just trimming off of the entire source here. So let's go ahead and debug print parse of source and just see what that looks like. Yeah, you just ignored every non-alphabetical character, which I think I'm kind of doing here. You are complaining because none of this stuff actually happens. So I'm going to silence that for now. Okay, 2, 3, 2, 5, 2, 7, 2, 9, 3, 3, 3, 5, 3, 7, 3, 9. That is great. I don't know why I avoided that for so long. That was like way easier for me to write than anything I could have done before. Ridiculous. Okay, so what I would like to do is I'm going to just like painstakingly just print out all of the moves from every single state in this example, and we might be able to pin down where we have gone astray. So we can do get next moves of this. Parse. I think this is just, I need to do an ampersand there. Okay, so, gosh, that's horrible. Let's do println. Okay, that prints out a little bit cleaner. And, okay, well, what I can do is maybe take Natty Bumpo's advice and do a debug of a particular state. So let's just do print fn print state, and the state is a vector of Amphipods, and that does not, that we're not going to even worry about returning a value here. I kind of want to convert this into a hash map. I've got some code that does that for me already. Let's call this by position. And then we're going to do for I in 0 to, how many rows do we have? 1, 2, 3, 4, 5. 0 to 5 for j and 0 to, how many columns do we have? 13 columns. Does that sound right? This is the 11th one, or this is the 9th one. 10, 11, 12. Okay, great. If is occupiable space, I, j. If it's not an occupiable space, or if it is an occupiable space, if by pos.contains key, ij. Actually, we want to look it up, right? If let some type equals by pos of the pos, then we are going to print character. And I need to actually make a character that does this. Get char? Gosh. Horrible. Maybe as char. There's probably a trait I can implement to cast this into a character. I'm not going to bother. A, B, we'll run backwards. C, and D. I probably could have written a parse function that also goes backwards from this. Not a big deal. What a hot mess this code is. Type dot print bang, else print bang a dot, else print bang here. Yeah, I never actually implemented the display trait before. Rust display trait. Okay, yeah, it's a fair amount of code, but it's fine. Okay, so what was I trying to do? I was actually just trying to print the next state. Get next moves. I actually have to materialize the move, right? We're going to actually write a function that applies our state, and I think we actually wrote it already, right? It is this nonsense. Print a new line after every row. Okay, so we're going to print state of the apply move of, we actually need to get the initial state. Okay, that's a bit of a mess, but it's because I need some new lines in there. I'll just print one before all of these. I guess I could just do println with an empty string. It's maybe a little bit easier. Okay, there's some extra hash marks in here, but that's okay. The extra hash marks just represent this empty space. It's not really relevant here. So we have BC. I think I wrote my print function correctly there because it's printing out what we were expecting. And then the next move that we want is this one. Does that appear? Okay, so that move appears here. Okay, so what we want to do is, we know that this move is the thing that we want. So we're going to just go ahead and paste this here. Oh my god, I wish there was a way that I could get it to not auto indent. But I can just manually fix it. So we want to go from this move to this move here. Which is basically C moving to this position here. Or C moving to its home position here, which is actually in our simulation going to be two moves. It's going to be C going to this. Oh. So Natty Bumpo, I don't know if you're still with me here. But we made it so we can only move to a hallway spot. So you know what, this is going to be fine. This is going to be totally fine. So we're going to go from this intermediate state, and what we just want to make sure is we have C being able to move to any of these two spots. Oh, really, it's just going to be this spot right here, right? This one right here. That's the only one that it can legally move to. So this is our initial state. And then we want to have one in here where C moves here. So that's this one. Okay, so we've been able to produce that move correctly. So that's the next state we're starting out as. And now we want to make sure that it moves into its home spot, because that's what's going on here. So this was the state that we started with. Good. And literally the first move is for it to move to its home spot. So far our get next moves function, which is what we're testing right now, is doing what we want. This is actually something that I probably can just like write some unit tests for, but I'm just laboriously walking through it right now. So now that we're in this state, we want to make sure that we find a move where B, this guy, or actually what's happening here is B or D moves out of the way and then B moves in, right? That they basically have encapsulated a couple moves in this step here, right? D moved out to this position here, and then B moved into this position here. Okay, so the first one we want is D to move out. That's this one right here. And now we want B to move into its appropriate spot. Wait, I copied the wrong one. The one I want one I want, I don't actually see. What we want from here is this D to move over here. You see it. Okay. Oh, it's this one. Right? Okay, and then now B will move into its appropriate spot, which is this one here. And that gets us to this. So the next move is the leftmost bronze moves into its own room. So this one, actually the next step is we want this B here, this one, to move up to here, right? And that is this one. I have the feeling that we're not going to find an issue here. Yeah, so we've gotten to this state, which is the same as this. All right, just a few more we have to just try to like painstakingly slog through. And the move we are looking for here, both Amphipods and the rightmost move into the hallway using 2003. That is D and A. So we want D to move this, the second D to move to this one here, and the A to move to this one here. So we're going to process two in sequence. It's this one. And then we want A to move out. That is this one. Both Amphipods move into the hallway. And I believe we have matched this state here. And then the desert ones will move down. Yeah, okay. It's this one. Okay, I believe I have found an issue, unless I'm missing it. For some reason, oh, I just haven't saved it and run it again. Whew, that was close. So now, okay, this is the state that we're going for. And then finally, will we get to this one? I got a good feeling about it. Yeah, so the first possible move is to finish correctly. All right. So one other thing I'm just going to do is I'm just going to copy this. This would have been a good solution to unit test properly. We're going to parse this, and I just want to debug print whether this is finished. It is finished. Okay. Okay, why did we go through that exercise? We went through that exercise just to make sure that get next moves will at least incrementally get us to the solution that we want. So for this example, for this initial example that we're working with, we should, running Dijkstra's algorithm, get to what we want. But we're not. So that means that I've implemented Dijkstra's algorithm incorrectly. Yeah, we're hitting this unreachable down here. Okay, so there is just a bug in the way that we've implemented this, which is actually kind of what I was hoping. If we had an issue in get next moves, that's, I think, the finickier piece of this whole thing. Okie doke. We put on the initial state with a cost of 0. We pull it off. We're definitely not finished. We advance past that. And we go to this thing, which is basically saying, in our initial state, did we put something into the lowest cost list that gives us a lower cost? I'm still not convinced that this is necessary. And if so, we can continue. Next, we will grab the next moves. For the current state. The move is consisting of which amphipod we move and its new position. We grab the previous amphipod from the previous state. We clone the previous state, and then in that clone, we update that amphipod to a new amphipod of the same type, but using the new position. We calculate the cost of this new state, which is just the previous cost, plus however far the node traveled, times however much that particular type of amphipod costs to take one step, right? And if this next state exists already in our lowest cost list, we want to get that previous cost, and we're only going to consider this move if it's cheaper than what we did before, right? So if the previous lower cost is less than or equal to the cost that we just determined, there is no point in us continuing. Otherwise, we did find the lowest cost to achieve this particular state that we've seen so far. And so therefore, we're going to clone it and stick it into our... Actually, this should be cost. Aha. So I think going over this word by word is great, because we are undervaluing the move to this state. That makes sense. Okay, and then we push the new state with its cost into our priority queue. And it's slow. I'm going to try running a release. $12,521. So that is the correct answer. It is awfully slow. But it works. So let's just try it on my input. and we're going to let it cook. So some of the irrelevant moves that we're making is that we are, for example, moving from the hallway into like the first spot in a room, even if the second one is unoccupied, right? 14,415. Hooray, we got the right answer. That's what we were expecting. And so the second half of this puzzle, let's check it out. You notice that the diagram they handed you was actually folded up. As you unfold, you have an extra part of the diagram between the first and second lines that insert the following lines. The amphipods still want to be organized in rooms similar before. In this updated example, the least energy required to organize these amphipods is 44,169. Okay. This is cool. We do have to readjust the parameters of this a little bit. A lot of these like hard-coded positions here need to be expanded. One of the interesting things that I'm doing that I think is probably causing this to be expensive is that I'm kind of rematerializing this vector every single time I call all hallway spaces. So I could try throwing that into a constant. How do I do that in Rust? Like Rust global vector. Could just make it an array, right? I can do global arrays, and this doesn't need to be a vector. So let me go ahead and commit this code. You should use cargo flame graph and actually see what is taking so long. Yeah. I haven't used cargo flame graph before. I'd be really interested in trying it out. Is it flame graph RS? Is this a more reputable one? Yeah. So I wanted to grab this. And then if I wanted to actually run it, it's a little DSL here. What in God's name is it doing? Is this a git pull? Like, what is all these... You know, it's probably updating some local repository, right? This is exciting. The world of kind of like granular command line profiling tools is a total mystery to me. I can profile in like Web Inspector. And I can profile when I think essentially there's a graphical tool that's given to me. I'll need to run as root because dtrace. Yes. Do I have dtrace? Does it come with macOS? Or does it come with this? Does it come with FlameGraph? Looks like I've got it. Okay. So does this mean FlameGraph is just like in my path now? Okay, no workload. Fine. I'm into it. So what I would like to do then is if I have to run as root, there's a sudo here. That's a fine name. And then it is target. Should I do the debug build or the release build? What do we think? Probably we can do the release build just because it'll run an attractable amount of time. But I'm guessing though that the release build call stack is going to be significantly harder to read. I'm going to try it anyways. So let's actually go into day 23B. Let's go into the project folder and we will do target/release/build, and I think it's called just day 23. I set up this whole Rube Goldberg a while ago, so I don't remember what these things were called. Oh, wait. Oh, it's release. Why did I think there was a build in there? Oh, it's because I was skipping this. So it's actually just sitting there at the top level. Why is this called day 23A though? Did I screw up? Just running it, making sure it does the exact same thing as before. Very pokey, isn't it? You usually use cargo flame graph. Okay, so that's this thing. Oh, I need to actually be in here. So cargo flame graph must be a different tool than just flame graph. Building without debug info, enable symbol. Oh, okay, this makes sense. Still not sure if I want to do the release build or not, but let's go ahead and just do this and see what happens. Is it cargo build release? I don't remember what I did here. Relax. I'll just do my make file. It's all in there. It's the problem when you write scripts and things, you don't know what happens on a granular level. Also, cargo flame graph root on Mac OS. Does that mean I don't need to do sudo? Will it try to sudo for me? Bad pattern. What is the is this bracket here just saying that it's optional? Is that what they're doing? Because like when I saw that, I was like, what, did they write a whole DSL for this command line? Or what if I just didn't even bother with that? And let me get rid of this no inline. This is all mysterious. I'm just gonna like freaking do the bare bones call here. Gotta type in my password. I wonder if there are people who can basically sample the WAV file of this video and hear me typing my password and compare it to the way that all the other keys that I'm typing sound like, and because they'll know what keys are like going into the computer because they'll see what's printing out in the IDE, and then somehow figure out the password of my computer. I bet it's possible. FlameGraph SVG. What is this going to do on macOS? It's going to open Pixelmator Pro. That's awesome. Fantastic. Hunter2 sadly is not my password. This flame graph does not go deep enough. Look at this. Is there a way I can set the granularity or depth of this? I'd like the deepest frickin' flame graph that I can get. A browser would work better. I completely agree. So what's the is there like a flame graph dump? I got an SVG. Okay, so there's some interactive tool. If I just call cargo flame graph, is there a flag that I can use to run it interactively? Cargo flame graph browser. Oh, we just opened the SVG in the browser. Oh, I see what you're saying. So the SVG itself is like this gigantic XML document. That's what we're drilling towards here. It's probably running CVS as well, CSS in there as well. Oh, fantastic. Okay, so this is the actual program. Click in there. Has path is slow. Hash map insert. Fetching from the hash map. malloc free tiny. So it's kind of this thing that we can improve upon, but these hash map insertions are kind of like... The issue is that I'm basically using a fairly large key. Do I want to become famous? I do. By followers, primes, and viewers. I'm kind of tempted to go to that link. What's going to happen if I follow that link? I'm just going to go into an incognito window. See what happens. I don't know, like... I don't know, Dom, if you're still in the chat, should we be flattered that we're getting spammed like this? Is this a badge of honor? Okay, so it's not... It looks like the cert certificate is actually invalid. I wonder what they're actually even sending us. It says here that this certificate was issued on it expires in a month or so, but it looks like the intermediate cert expired a month. Like, you'd think the spammers would at least try to make this easy to get to. Like, yeah, we've made it. I agree, Dom. We've made it. They couldn't even they could even friggin' let's encrypt this stuff, right? If they're really just trying to fish me. I want to go anyways. Let me go. This is probably gonna log for shell me, right? Like, I'm just gonna be I'm gonna die here. Oh, okay, I can actually buy followers here. Is this just a scam though? Are they going to are they just gonna take my money, or my Bitcoin as it were, and then just not send me actual followers? High quality real names. What does that mean, real names? Are they just scraping LinkedIn or something, or one of those weird yellow page identity databases that are out there? I do want followers. I really do want followers. So, yeah, I don't know. Nathaniel Bumpo, FX hashmap would help with performance since it's not cryptographically secure, right? So what is hashmap using? Is it using SHA-256? I guess it's whatever provides resistance against hash DOS attacks. Fine. I mean, I almost don't really need a we don't really need a cryptographically secure hash, right? We just need like even like a CRC would work. Um, so I think what's making this slow though is just like this freaking payload is really big, right? It's a vector and it's just like a big thing. Now haspath itself is also just being it's just like contains key. It's all these like hash table operations that seem to be taking a while, right? Um, and unless we can think of a way of like, I guess we could just like we could get another dependency to do it, but you know what? I'm not too fussed by that. I think another thing that we could think about is like are we are we providing too much information in this state? And I think the answer is no. I think the state, all the information in there is like 100% necessary. It's like whether or not what type each item is, and then also what their position is. I would say the thing that is causing us a little bit of grief, and I mentioned this before algorithmically, is we are treating the state where, because each amber amphipod is assigned to a specific location in the vector, we're treating it as two different states. If both amber amphipods actually occupy the two same spaces, like two spaces that are the same on the map, but they've swapped positions. And I actually think that those two states are equivalent. Can we call new states? Can you specify what you mean by culling? Like, what would be the culling mechanism? Now, we could do something like A star, right? Like we could improve Dijkstra by just like fudging the cost a little bit by saying, I actually think that like this particular move is better than this particular move because it gets us closer to our result. Coming up with a heuristic for that is maybe a little bit tricky. Is it just the Manhattan distance of, because it's not just the Manhattan distance of one node getting to its home position. It's like, how far are we, like what is the total Manhattan distance for all of our nodes to their home position? So that actually might not be a bad way to fudge this, right? We could sort of mess with the cost a little bit by adding some kind of bias onto it. But we'd also need to pick like a weight for that bias. And I'm not 100% sure whether that's, like, we can try it actually. I think maybe what I'm going to do right now is at least try to finish part B. And then we can think about our opportunities to optimize. What is this? Homeroom positions. So I said before, like, we could try to like make homeroom positions an array, or and not make it a function that we're rematerializing the vector every single time. But honestly, in terms of our total runtime, it's just not occupying very much. So Natty Bumpo's suggestion to just like look at the flame graph is absolutely the right thing here. Okie doke. Well, if this is where we're at, I'm just going to go ahead and try to write the new thing. And I think the new thing is going to just like take way longer, and it could be that the optimizations are going to be necessary. But what is the actual new thing? They are saying that we actually have to add this sucker in the middle, right? And I want to make sure I'm working in B here. Is that right? Yes. Okay. So there's a fold between the first and second lines of text that contain Amphipod starting positions. We are going to add this here, right? And now I think we need to change this stuff. I'm not going to worry about my debugging code for the time being, but I do need to update some of this other garbage. Okay. So if it's a room space, so we're gonna say if position 0, if position 0 is less than 2, or position 0, or what's the maximum row? This is row 2, this is row 3, this is row 4, this is row 5. If 5 is less than position 0, so this is a row, we return false. And then we just return whether position .1, and we'll just return this whole horrible thing, because we didn't change the number of columns, right? So I think that's the update for the room space. And then our homeroom positions are going to be updated because we have a bunch more rows. Dang it. I'm just going for it. And this is 5. Oh man, this is not the best coded solution that I've provided for Advent of Code. But we're not going for perfection. The joy is in the doing, right? I don't think is hallway space changes because we didn't affect the hallways. This function is a room space, basically saying if we are above row index 2 or we're below row index 5, 2, 3, 4, 5, then we are not in a room space. Otherwise, if in the columns we're 3, 5, 7, and 9, then we're good. Did I hard code any other kind of geography into this? All the Manhattan distance stuff is the same. So I think this is going to work. It's just that like this might be like exponentially slower just by adding some extra space. But I'm going to just go for it. Your code was about 300 lines long without a parsing function and using the pathfinding crate to do Dijkstras. Okay, cool. Well, you were probably doing cooler stuff than me. I'm like a little bit less than 300 with a parse function and then like Dijkstra explicitly spelled out here, but there might be cooler stuff that you've got going on. We are just going to let this bad boy cook. I didn't even run on the sample input. So we're just gambling, people. And this could be just like an order of magnitude more complicated. I mean, what is Dijkstra? It is like, what is the n in its complexity, right? Is it the number of initial positions? Just had Natty Bumpa's solution had giant functions, hard coding a bunch of things because it's easier just to hard code than thinking of an answer. I hear you. Natty Bumpo, you worked on this last night. Does that mean you're on the West Coast or somewhere roughly near the West Coast of California or West Coast of America? I guess it was basically nighttime for everybody when it dropped. Well, no, that's not true. If you're like in Japan, it drops in like the afternoon, right? Central time. Okay. Right. So Central time, that means you were getting the problem at 11 p.m. I used to try to be really on top of this stuff. I was looking back at my leaderboard performance, and I really suck at this. Oh, you finished at 4 a.m. Well, I'm flattered that you finished at 4 a.m. your time, went to bed, got up, and then somehow found your way to our stream again to watch me work on this problem yet again. Potentially, this is just background music for you, though. So I think my best performing year might have been 2015. No, that's really bad. Maybe 2016, where I don't think the first problem really matters. The first problem is always like FizzBuzz, but I actually I got like perilously close to the top 100 in the world on one of the problems. And then, as you can see, I like progressively like dropped off, and that was probably because I was just finishing these problems like a week after it, a week afterwards. Natty Bumper, you've been refactoring things on and off all day. That's cool. I'd be interested to know what people are doing to really make this faster, because like my thing still isn't done. So clearly, I need to do some kind of optimization because this is just ridiculous, right? Is it okay if I click on your link on stream? Well, I guess you gave it to me in chat, so I'm going to do it. I'm going to do it. What MacBook do I have? I have a MacBook Air with an Apple Silicon CPU. So it's pretty fast, single-threaded, which is what we're talking about right now. Oh, this is cool. Oh, I see. Is the gray splotch here part 1 and the yellow part 2? Or this is actually just everybody, right? This is basically we're looking at samples for everybody. And so this is this year's. Go back to 2016. What day was I boasting about? I don't even remember. It doesn't matter. Some of these are really interesting. It's interesting when the times mix over a long tail like this, right? Like day 19. Do I even remember what we did day 19? I don't. But yeah, this year has been interesting because I even felt this, like starting from a couple days ago. It started to get like really brutal, like the drop off, like the difficulty spike between part 1 and part 2. And you can basically see it being visualized here. Natty Bumpos takes 40 milliseconds on an M1 Pro for part 2. Well, this is taking like way longer than 40 milliseconds, right? So it's possible that like somehow your Dijkstra is just way better than my Dijkstra. And if we go back to it, I mean, we're just doing a shit ton of hash operations. And I actually think that it's the key calculation, right? Well, make hash is actually not a big part of this. If I go into this, contains key, it's writing a value into the hash table. Maybe it's just got a ton of states, right? Ugh, back button. You broke the back button. Oh, this is the hasher. So we're missing some. I think we're missing some things in the call stack here, or it just isn't able to sample into that because reasons. But I think this hash write is actually the calculation of the hash. So I like maybe what I said before about we're just trying to hash really large objects is part of the problem here, or at least like it's like half the time that we're spending here. But this is just not. It's not having it, right? Right now, there's like steam coming out of my computer. If it had a fan, it doesn't have a fan. So I bet I'm just getting throttled right now like crazy. Doesn't help that I'm running OBS at the same time, but you know what? These are modern computers. It should be able to handle it. Am I running in release? I am running in release, yes. And the flame graph is also a flame graph of our release build. Did I just close that like a fool? Or did I just... I think I did close it. One of the things that makes this a challenging thing to optimize is the widespread between step costs. The fact that the desert thing costs 1,000 times what an amber thing does. It means that this severely disincentivizes moving any desert unit, any desert amphipod. Is that I already forgot what these creatures are called. Yeah, amphipod. The fact that the cost is 1,000 means that like it could be that our solution really demands that we move a desert amphipod a couple of times, but because it costs 1,000 to move it, the priority queue is not going to get to those moves until we've done a shit ton of other irrelevant things, which is what makes Dijkstra's algorithm a little bit rough here. Now, we could bias that by maybe adding Manhattan distance in, like how like, but again, I don't know how to weight that. Like what we could do is basically take the Manhattan distance of every object to where it's supposed to be and then add it in there. What's your input? I'll see how fast my solution is. Okay, I'm going to try to paste this into chat and I'm going to see what happens. I apologize in advance if it's going to give us some nonsense. And in fact, why don't I actually fill this in with some extra hash marks to make it so that it doesn't get corrupted too crazily. Oh god. I'm using a chat client called Chatty, and it is not pasting very cleanly. So why don't I just, if I'm done fooling around over here, I'll just grab this input and I'll give you these characters. Yeah, you figured it out. DCCD cab. Oh, DCDB. The other thing is I think this should be less than or equal to right here. But the problem is we have an initial state problem where yeah, you ran in what, 45 milliseconds, is that correct? That's an exciting flex. Yeah, I wonder what the pathfinding crate is doing that is fancier than this. Because this seems like pretty straightforward. Could be that the priority, like, it's all the hash map lookups that are costing me, right? That was what we decided. Nope. So if it's not the hash map, if I'm kind of like not really able to optimize the hash map lookups themselves, what it is, I'm just doing too many of them. And let's actually take a look at where this is actually happening, right? I am creating a bunch of hash maps. So if we wanted to talk about it a little bit, one of the things I did is I said, hey, in order to get the next moves, I'm going to take my vector of amphipods and I am going to create a hash map out of it. And then do my thing. But in principle, I could just make the state a hash map. Now, can I hash a hash map to be my state? Or do I need to dig this out into and make it a vector again in order to be able to run it? Hash rust hash of hash map. Somehow I don't think it implements it. Rust, can I hash a hash map? Somehow I think this is going to be a hard thing to Google for. Oh, implementing the trait hash for hash map. So the fact that somebody's asking even three years ago makes me think that it doesn't exist. Yeah. I mean, I guess there's really no reason why it should be hashable, right? Because there's no defined ordering between. I don't think like ordering matters for either keys or values in the hash map, so it's kind of arbitrary how you would hash it, right? Mm. I wish I had more of the call stack here. It would be nice, wouldn't it? Like, which insert are we talking about? Yeah, hash map iteration order isn't guarantees the hash won't work. Yeah, I mean, it's not even so much about like, yeah, I guess iteration order is one way of saying it. It's just kind of like there's no built-in semantic to a hash map that says that ordering even matters, right? So it's not only that you don't know what the ordering should be, you don't even know if ordering you should have an ordering in the first place. Pathfinder uses index map. The index map is a hash table where the iteration order of key value pairs is independent of the hash values of the keys. I think in our case, what we would want out of hashing a hash map would be, oh, my computer's so hot right now, in both senses of the word. But what we would want for hashing our state is we would actually want to order it by. We want a strict ordering of our like our keys. And that's what the state would represent. Okay, so I don't think this is going to finish in a human amount of time. So I'm going to cancel it and lag check 2:20 p.m. exactly. Did I just stand still for too long and it just looked like the video was lagging? Okay, so let's try to do something to sort of reduce the number of times this is going to run. Or the number of times this is going to loop. So one thing I would like to try to do is, well, there's two sites of optimization that I can think of right now. One is that this really should be less than or equal to, but for some reason it worked last time, but it's not working this time. What this is saying is that somehow when we pop something off the priority queue, something else might have already gotten inserted with a lower cost. I don't understand this. if there was something, if this state got pushed on to the priority queue at a lower cost, it should be the one that we popped off of the priority queue and not this one, right? Because we insert onto the priority queue the same time we insert into lower costs. I've been lagging for a while. You know what the lag is? Is that I'm running my friggin' program, right? How's my memory usage? Good question. Memory usage is okay. I did cancel my program. I'm hoping that it'll catch up now that I'm not running infinite spin loop on my computer. Although you'd expect this to only just occupy one core, right? Okay. I really don't understand this case. Like, if we go to the binary heap docs, is it this one? Yeah. Nope, that was the same one. So this is their sort of their manual for the binary heap built in. Their shortest path algorithm, their distance is essentially equal to my lowest costs thing. So they're saying, okay, we're going to pop off the priority queue. We're going to get a cost and position. If we've reached the end, we're done. Otherwise, if the cost of the thing that we popped off is greater than the distance to this position, and it says in the comment, important because we may have found a better way, we want to skip this. But the way that they're updating the distance array is the same time they're pushing on to the priority queue, right? So if they pop off the priority queue, they should be getting the lowest possible cost inside the priority queue, which means that distance next position should have its lowest possible value. So I don't understand this condition. Like, if you popped off of this priority queue and you got a value out of, you got a cost value that is higher than dist position, that means that something else wrote into dist position between you getting pushed onto the priority queue and you getting popped off the priority queue. But if they wrote a lower cost, you would never get to this line in the first place. I want to write them a letter. This seems like it's like wrong, right? And in fact, I think if we look at like Wikipedia, Dijkstra, I can never spell this. I always put the S in front of the J. I don't include an I. If we look at this algorithm, they say, let's pop up the priority queue. Did I reverse the cost? That is a great question. That is always something we want to be able to determine here. Oh, this is saying it's a max heap, so you might be right. We want a min heap, don't we? So this should maybe be self.cost.comp other. Does partial comp need to be changed? This looks like the same. Binary heap is a max heap by default. It's a max heap by default. So we actually do want. I think the reverse ordering is what we wanted, right? Notice that we flipped the ordering of the costs. Yeah, we want a min heap. So if we want a min heap, so if it's a max heap, it's going to take the thing that sorts after. What is the sorting enum again? What are the values? Is greater. Okay, so it's going to take the thing that is greater first, right? So the reverse is what we wanted, right? Yeah, and I don't think this is any different than what was there before, right? So I actually do think that the reversal that we had there was correct. Oops. Shoot, I did not. I hit undo too many times. I just want to make sure I did the right thing here. Row 2 has 3579. Row 3 has 3579. Row 4 has 3579. And row 5 has 3579. Okay, cool. I somehow lost the prompt. What is today? Today's Thursday? Just trying to determine if I had anything else to do today than just work on this problem. All right, I am going to take a quick break, a couple minutes, get a glass of water, and then I will be back, hopefully to polish this sucker off.
5 minutes later.
And we're back. Thanks for everyone's patience. Looks like while I was away, Natty Bumpo left a comment here. One thing in the pathfinding crate that they do is explain with this comment, we may have inserted a node several times into the binary heap if we found a better way to access it. Ensure that we are currently dealing with the best path and discard the others. So we have that in our implementation, right? So if you push a node into the priority queue, it may have a really high cost, right? However, you're also pushing the state into this lowest cost lookup table with its cost, and then right here, we are actually just saying, hey, I'm going to ignore it if we had got it. Okay, so this is why this is necessary. We may be trying to do something. We may be just like doing this loop unnecessarily because we already tried to handle it. I get it. Now, that being said, I don't think this saves you that much. Because let's say you already did handle this with a lower cost, but you ignored this little optimization here. What's going to happen is you're going to go into this loop. You're going to reproduce the same set of moves, the exact same set of moves that you calculated last time you came here. But you're going to have a higher starting cost this time. So by the time you get down to this check, it's just going to go, oh, I'm just not going to insert them because I actually already inserted the exact same thing that you did before. Yeah, they don't use a hash map for the lowest cost table. They push a tuple into the priority queue, the cost, and index. And then they look up the value in their index hash map. That is very interesting. So what you're saying what we can do is, let's just say, let mute all, like, states, plural, is equal to the hash map of a vec of amphipod, or rather it's an index, and let's just call it an I64, and vec amphipod. This is just hash map. Why am I overcomplicating my life here? So this is the states. Don't we need a reverse lookup table though? So our node then is just going to be a state index, right? And maybe we'll just make that I guess it could just be a U size theoretically. Where did I even put node? It's probably like way up here. It's just in some arbitrary position. They can look up both by index and state. I think I'm going to need that too. But let's just take a look, right? So we've got our state here. We actually want our list of states to be initialized here. Natty Bumpo, I'm going to follow your advice, and we are going to make a vector. But I think we're going to need the reverse lookup as well. Actually, this is just vec bang of state. And then we're going to push this ID here. I guess not having to clone is nice. And that ID is 0, right? And then the lowest costs here of I64 is 0. And then we're going to pop this node off, and then the actual state, I'm going to call this start. The actual state is we're going to look up in our states and then grab it, node.id, right? And then this is going to be state. Cannot be indexed by I64. I think those I64s just need to be U sizes. I think this just needs to have an ampersand in front. So if we are finished, we'll just print the cost. And we're done. We're going to get the lowest cost by looking at the ID again. In get next moves, we're just going to pass in state. So here's the trick. Yeah, we only need a hash when we update the state. So here's the trick is we do need to make sure that this next state, if we've seen it before, we get the previous ID, right? Which is why we need the reverse lookup table, right? So we'll have like let mute state IDs by state. A little bit painful to type, but it's a little bit clear what we need. Vec Amphipod into U size. Actually, this is just hash new. I'm just brain farting my way to oblivion right now. So when we insert into states, we also want to insert into state IDs by state. And we're going to add the start state as the key and 0 as the index. And in fact, because I'm annoying, I'm going to actually just write these two things out very explicitly. I guess I just have to push here, right? Start. That way this is just a little bit parallel, right? Okay. So what we're going to do here is, now that we've modified the state, we need to look this state up in our if. We basically need to get an index for the new thing. So let next ID equals, and then we're going to match on state IDs by state get of next state. And if there's some ID there, we return the ID. Why is it giving me an I32? Is this not usize? Oh, it doesn't know yet. Otherwise, if there's nothing in there, we need to update states. We'll get the length of states. Actually, we'll just return ID -1, and then we need to push onto states the new state, right? Next state, and then state IDs by state is equal to, well, we'll insert next state. Oh hell, let's just let new ID equals this. New ID. New ID. So that's our next ID. Next ID. And our node here is ID next ID. All right, so that's certainly cleaner code, right? Oh, and then we need to clone here. And that is that. All right, how does that feel to everybody? This is a nice kind of optimization here. What are we doing? States, node ID. Can I move out of this? I think this just needs to be a reference. Oh, because we're modifying states, this actually needs to be a clone, I think. States that push start. Okay, I gotta add these clones. It's just the nature of the beast. All right, I don't know if this is gonna make it that much faster, but we can try it. I mean, what we can do is actually just run it on the previous day's input, or the previous problem's input, and just make sure that it's doing the right thing. Always do the right thing. Oh, I don't have an input file on this. I just pasted it in there. Come on, Jeff. Hello, is your implementation a priority queue? It is. Thank you for asking. I actually don't know of a different way of doing it. I think depth of search might be faster. Depth first search with maybe some kind of deny list to make sure you're not repeating states. So this is actually slower than before. But what that actually suggests to me is not that we made it slower. I think we just broke it. Like, we introduced a logical bug. I wonder how expensive the clones are as well. We're cloning twice in a loop. We're cloning here, and then we're cloning in here. But we kind of don't really have another way around that. Yeah, this to me feels like we've just broken it, right? We somehow not successfully. We're not successfully getting the lowest cost thing anymore. Either that or my recompile didn't actually recompile. I am modifying 23B, yes. So let's talk through it again. That helped last time. So the update here is we're referring to our states by IDs or indexes into a vector rather than by hashing the full state. I think that's a really nice improvement. We pull a node off of the priority queue. We use the ID contained within that to pull out the state. We have to clone it because if we just use a reference, we're going to have an immutable reference to the overall vector, which means we can't push into it down here if we need to. So we've got to clone it here. This early out is just saying, okay, did we actually reach where we wanted to go? And if so, we're done. This prevents us from processing something that we've already handled long time ago. And now we actually take the state that we pulled off our list of states. We generate the next moves from it, and it basically tells us which Amphipod to move and what its next position would be. This encodes all of our complex rules. Am I tracking visited nodes? Yes. So the visited nodes is this thing here. It is a hash map of the node ID and how much it cost to not visit that node, but to even just like consider that node and stick it into the priority queue, right? And we are checking that lowest cost thing twice. We're checking it when we pop off the priority queue. We're also checking it before we attempt to push something onto the priority queue. Is that UberX? Does that satisfy your question? Okay, where was I? Narrating through this, we were talking about this. Okay, now we get all the next moves. We have kind of painstakingly gone through our business logic and have assured ourselves that this works, at least for the case that looks like this. What if you get an identical state with a different ID and higher cost? Do you prune those? So, kind of, but no. So when we talk about identical state, it's probably useful to talk about how we're getting that identifier. So the way that we're doing that right now is here. So we have a thing that indexes our states. Okay, so first of all, our states are vectors of these things. So it's a type and a position. And importantly, in that vector, if, for example, Amphipod D here starts off as the 0th position in that vector, it's always going to be in the 0th position of that vector. So technically, we do have duplicates that we're not pruning, which is to say the state where you move this other Amphipod D into this position, which technically isn't possible, but maybe somehow it is. But basically what I'm saying is that if there are like mirror image swaps of these, I am not pruning those. And that potentially is a problem, right? Maybe I should just try to eliminate that case so I can stop thinking about it. Yeah, so the IDE is derived from the state. Let me show you the code. The code is down here. These are all the states that we've accumulated so far. And then we actually have a reverse lookup table that says, give me the state ID or the index into that state vector given the content of the state. And this is a hash map. So we're basically hashing the state, getting the index into the vector. If it's already in there, great, we found the ID. Otherwise, we need to actually introduce it. It's not perfectly deduping states, but I think it works. I agree, although I'm a little bit worried about this kind of like swapping situation. Although, I would actually need to really think about it more because I think I'm making the assertion or the guess that you can swap letters arbitrarily as long as they occupy the same two positions in the map and they would represent the same history. But I think that should be fine. That should be fine, right? But that is not trivially, at least to me, it's not trivially true. Like, I haven't really thought through it. UberX feels like it's not worth differentiating the A's and B's, etc., to be honest, right? Well, I am differentiating them. That's actually the funny thing, is that my implementation does differentiate them, right? So I'm actually curious, is it worth accounting for the fact that I'm differentiating them and then not differentiating them, right? I think the question is, A, is it correct? And B, is it worth it? Or maybe it's kind of the opposite, right? Like, is it worth it in the first place? What do I think it's going to buy me? And secondly, is it actually correct? I don't know. Those two questions I think are go hand in hand. The reason why I think it might be worth doing is that there are a lot of different permutations of this exact image here, right? Like, you could have one where D, like if I gave these like numbers, or let me actually write this out, but use capital and lowercase, right? I wish this were a little bit easier to read. So the question is like, I'm getting a lot of quote unquote identical states if I am trying to differentiate between the uppercase A and the lowercase a and the uppercase B and the lowercase b, when that doesn't matter. Because if you think about it, there's like a lot of different permutations of this state, right? I could do this. I could do this. And so on and so forth. Yeah. So this actually could be pretty important. Again, I'm not sure if it's correct or not, but oh, you know what? This finished. It's finally freaking finished. 14,415. That is the right number. Okay. The left D could go to the right and the right one to the left. Those are identical but different. Are you saying that it is meaningful that they're different? Or that it's not meaningful that they're different? Because they do represent different histories, right? They do represent different realities of the world. I'm also, let's put aside the fact that it's not really possible to swap those two. Like, you can't, like, because of the rules of how you can move these things. Some of these things aren't even possible, right? But you can imagine a situation where you're just like up in the hallway, like everybody's up in the hallway up here, right? And you could swap things around pretty arbitrarily, right? But I think y'all are picking up what I'm putting down here. Yeah, UberX says that it's meaningful that they're different because they represent different histories. So that's actually what I think what we're saying though is that it is not an optimization to try to improve upon this because it is actually incorrect. They can be swapped in the hallway. So let's talk about that scenario. I don't know if this is getting us any closer to our solution, but it's just fun to think about. And the name of the game is fun, right? The real prize are the friends we made along the way. So I guess the question is, let's say we've got this situation. Does it matter to us that we are differentiating these two cases? UberX says, sorry, there's a significant delay between video and chat. Yeah, I apologize too. I wish I could do something about that. I guess my computer's just slow. I think one of the things I can do is maybe OBS from a computer that is not the one that I'm running a super computation expensive program from. But I didn't want to fuss with it today. Normally that's what we do when we have multiple people on stream at the same time. But that's not happening right now. Sorry. So anyways, the question that we were kind of like just asking, which is I think maybe kind of academic at this point, is like, does it matter to us that we differentiate between these two cases? Well, they might have different costs if you arrive at that point. But maybe the question is, Does it actually matter to the future of this state? Yeah, does the difference matter to the future of this state that we make a distinction between the two? And I would posit no, right? Like these two might have different histories, which means there's a different cost to it, but the future set of moves is basically identical, right? Differentiating makes them dramatically slower if you think about it, because I'm not pruning. Like another variation on this state is if totally irrelevant nodes swap positions. So I could put capital C here and lowercase c here, right? So all of those different permutations are being accounted for. So I'm actually curious, maybe we should try to make our state a little bit more ordering independent. What's the right way to do that? It means that our state needs to not care what order they go in. So one way we could do that is in our state, we can always make sure that we sort by... We sort the state by their type and then their position at all times. Yeah, you can get away with differentiating them if you discard identical states with higher costs. Yeah, and we're doing that as part of the algorithm here, so maybe we should give that a shot. So what it means is that like anytime I generate a new state, like this one here, I need to sort it, right? So I generated a new state when I parsed, and then I generated a new state when I updated one here. And so what it means is I actually have to resort these. Okay. So I just need to add like a sort thing onto my Amphipod structure. Rust sort ord trait. Do I need to do partial ord as well? I always forget what the subtle distinctions between these two are. It requires equal and partial ord. Could I just... Is it possible to just derive partial ord and ord? I guess I need to derive it for type as well. And so now that we've got that, let's go ahead and sort parse. Sort this. Or maybe parse should actually just return it sorted as a service. Service to the reader. Sort res. Okay, so parse returns it sorted. And then when we update here, we've already cloned, so let's just sort next state. And this should get rid of any difference in what's identical. Is it going to be a meaningful speed up, though? I'm a little skeptical. What's a little bit disappointing is we actually made this... Natty Bumpo had a really good suggestion, which was to basically look up our states by ID rather than hashing them. But for some reason, that ended up taking way longer. Well, that was a bit faster. I mean, it's probably like 20 or 30 seconds. But it got the right answer. This is going to cause the video to lag a lot, is my suspicion. Okay, takes 30 seconds. So why don't we just try running with the real thing and let's see what happens here. I'd be curious to know if DFS is faster. It very well could be because I'm actually spending a lot. Well, DFS, you'd still need to do some kind of deduplication, right? And DFS would be faster if... I don't think DFS... DFS would be faster if basically it is prioritizing smart moves of the desert amphipods. Because the problem with Dijkstra right now is that we are doing potentially up to like 1,000 stupid moves on amber amphipods, when what we should be doing is moving this one. But because Dijkstra's algorithm is prioritizing the lower cost things, it's going to take it a while to get to moving copper and desert amphipods. And we could try to bias away from that. Oh gosh, even my mouse is kind of messing up right now. Is my mouse running out of batteries? I feel like I just changed the battery. But yeah, we could try to do DFS. Let's. I'm gonna try to run this on the actual output right now. It's kind of like taking a scary long time, so I don't know if this is gonna be. I don't know if this is gonna finish in a tractable amount of time. But while it's running, I can try working on a depth first search version of this. I believe this is the correct pasting of this. I'm just going to run this bad boy, and we are going to watch it cook while I create another directory. Okay, so let me ask you this for depth first search. How do you know that you've gotten to the cheapest path? Are you just literally exhausting the entire search space? Okay, so if we're going to do this depth first search wise, it's going to simplify the implementation considerably, I think. So fn best cost from a particular state. And what are we doing for cost? I32. So we're just going to enumerate all the moves from here. And then we want a cache of some kind, right? So we're going to have a cache, which is a hash map of states. And their best costs, right? Or is the hash map just stuff that we've already visited, so we just don't want to visit it again? Is it just a hash set? So let's go ahead and do this. We are getting a bunch of next states if the cache already contains the next state. We're going to continue. Otherwise, we are going to insert next state. I think we have to clone it, right? We do want to care about the cost of the state too, not just the state of... Oh, yeah, you're right, because we need to... So what you're saying is like let's actually get the best score so far getting to this point, right? And where is my cost calculation? So that's our cost. If let some prev cost is equal to cache dot get of next state. Okay, if there's a previous cost, and if the previous cost is less than or equal to the cost that we just calculated, then we can continue, right? Otherwise, we insert this state and we insert it with the cost. And then we want to get the best of the children. So let mute best equals I32 max. I wanted all caps max. Min max. And then what we're saying is like best equals best the minimum with best cost of next state. Passing in the cache. And the cache needs to be a mutable thing. And then we return best from here. Okay. Oh, my parentheses are kind of messed up. So we actually need a cost coming into this, don't we? Okay, so we have some really, really high value, and what we want to do is we want to loop over every next possible move in our current state. And this logic, yes, so for each of these amphipods, we are going to grab the amphipod, we're going to clone the state, we're going to update that amphipod's position to whatever it's telling us to move to. We're going to sort this just so we're getting rid of duplicates. We're going to calculate the cost of making that move by taking the Manhattan distance of how far we moved, multiplying it by that amphipod's step cost. That is the next cost for this new state. If there was a previous cost that we already cached using this next state, which is sorted so it should be deduplicated, and that previous cost is less than or equal to next cost, that means we've already done the work for this and we can just continue. Can I do this? Yeah, okay. Otherwise, we can actually insert into the cache nextState.clone. What is next state? Our caches should not be references here. Otherwise, we basically take the minimum of our current best and the recursive call using the next state. And then best cost here. This takes 3 arguments because we need to pass in the cost that it took to get to this point, which is next cost, right? With the cache. So that's our recursive implementation. And so what we're going to do here, and we actually need to know when to end, right? Because like we're basically going to say like, okay, well, we're going to get to some point where we actually end up in the finished state, right? So if next state finished is finished, or we can do the is finished check up here, right? If is finished state, we just return cost, right? That's our base case. That seems right. So that means all of this nonsense goes away. We make a cache, which is just a hash map. And then we just println best cost of getting to our state. The initial state costs nothing, and actually I can just pass in like a mutable reference to a new hash map here. I don't even need to store that cache in a variable. Oh, this is starts. So I like this a lot just because it's way simpler in terms of code. Will it blend? I'm stack overflowing. So this doesn't complete with the expanded input. I'm actually curious whether it completes here. I'm getting into like our. When did I start at this? I started around 8:30 a.m. It's around 1:20 p.m. on the West Coast here. So I'm getting into like the 5th hour of doing this, which is kind of poking up against the longest I've ever spent on an advent of code problem. There was one a few years ago that there are actually some problems I just never was able to solve on my own. I think one of them involved like these 3D cubes in space, like yesterday's problem, but you had to like count the amount of overlap between them, and it was really complicated. And I don't even think that the right answers were correct because I could come up with inputs that would thwart that. That one I never even finished. I just had to like look at other people's responses. There was one a couple years ago that was really fun where you had to like essentially model the flow of water down this like 2D level, so it felt like making a video game a little bit. And that was really fun. Okay, so what's going on here is I'm doing a death first search. It has not finished running. So if other people's depth first search did finish, what that means is that my number of branches that this is... I'm back and you're still streaming. Yes. We haven't really figured out how to solve the expanded problem. We've thrown a couple different things at it. What I suspect then is that maybe other people are producing a smaller list of possible next moves. which means that my problem is just basically expanding to something that's larger every single time we run a loop. When I ran this with my part 2 input, this just gets Stack Overflow. Okay, if your depth first search took like 4 seconds, maybe we can talk through how each iteration is expanding, and you can tell me what's incorrect. So this is this get next moves function here, and what we're doing is we're taking the state, which again is just a mapping of amphipod types to their positions. We're just creating a quick little hash map here that does the reverse mapping, so it maps positions to types, so we can do a quick lookup table. And then what we're doing is for each amphipod, we're taking their index and their data, which is basically what type are they and where are they currently. And then we're saying, are they in a hallway space? If they are in the hallway space, there are a couple different possibilities. We can say, okay, is their homeroom, which is the room that they're supposed to be going to, can I move in there? And if I can't move in there at all, there's nothing I can do. I'm locked to this space. I've got no options, right? Because I can't move into my homeroom, and I have to move into my homeroom from the hallway. Okay. Otherwise, my homeroom is friendly, so what I can do is I can go to either of my homeroom positions. Well, there's up to 4 in the actual state of this. And if I have a path to either of those positions, I'll go in there. Now, one thing we could change this to is that you should just move to the deepest possible position, and that would reduce some of our options, right? So that's what we can do for each amphipod that is currently in the hallway. If it's not in the hallway, then the amphipod is in a room, and it can move into all of the hallway spaces, right? Oh, this is interesting. So there are actually possibilities here. So this is actually incorrect here. I'm glad we talked through this. There's a possibility because of this that you could move into the top spot of your homeroom position, your homeroom, but then never actually re-enter your room, because then you might step back out of the hall. Yeah, so this is interesting. Maybe I should do the optimization where you go deep as you can into your homeroom. So if you're not in your homeroom, like if you're already in your homeroom, you should not leave it, right? So maybe I should check that. You say, in fact, you must go to deepest. Is that a rule, or is it just something where it's just like it's pointless not to go into the deepest one? Amphipods will never stop on the space immediately outside any room. Amphipods will never move from hallway into a room. Amphipod's starting room is not its destination room. It can stay in that room until it leaves the room. Once an amphipod stops moving in the hallway, okay, yeah. So let's just move into the deepest here, and let's do it that way. Did this even finish the depth first? Yeah, I got Stack Overflow again, so I'm overflowing. So destination here. What I want to do is actually get the deepest homeroom position, right? Okay, so to get the deepest one, we're going to get all of the homeroom positions. And we actually want them sorted by depth, right? Oh, you know what? I think I understand why. I think I understand why my simple example is going out of bounds. It's because I have too many homeroom positions. I've expanded the map prematurely, which is fine. Let's go ahead and move them to the deepest. Let's see here. Where was I? Get deepest homeroom position. So these are the homeroom positions. I am actually just going to reverse the ordering of these things so that we start with the deepest. What's the easiest way for me to do this? The brute force way? Nice to forget an amphipod once it's a destination room. I totally agree. Okay, so now that we've done this, we can paste. And the thing that we're changing is these threes. I think I messed up. I'm sure there's a much more graceful way of encoding this. But bronzes go into column 5. Coppers go into column 7. Oops. Desert goes into column 9. So we get the deepest homeroom position. We'll just go to the homeroom positions. These are now in depth order. And we're just going to say if map.contains key of destination. If it doesn't contain it, we're going to just return some destination. Otherwise, we return none. And this is just type. So if the homeroom is not friendly, maybe we can actually combine these two calls together. I don't really care. So if you're in a hallway space, the only thing you can do is move into the deepest possible position, right? So it's basically if let some destination equals get deepest homeroom position of apod.type with our current state, our current map actually, yeah, state. Then res.push I destination. Sweet. Okay, that is it. And maybe to simplify this a little bit, we'll do it like that. So if the homeroom is friendly, so if the path is clear, we actually need to know if we can move, if we actually have a clear path to this, right? So in fact, we need another thing here. If has path apod.position destination state. If we have a path to that deepest thing. And what friendly means is that it's either all empty or it's all filled with my friends. Otherwise, you're in a hallway space. Sorry, you're in a room space. And we actually want to ignore... We want to ignore any amphipod that is already in its homeroom position and at the deepest position. Is it possible for an amphipod to not be at the deepest position it can go to in its home room? I think the answer is no. So if an amphipod is already in its home room, well, we could have a situation where you're in your home room, but the home room is not friendly, meaning you're not at the deepest position in your home room because because of the initial state, right? And that is the situation with our friend D over here. So how do we account for that? The logic is a little bit subtle. I think we can say that if apod.pos All right, there's an issue with my type checker right now because apod.type homeroom positions.contains apod.pos. Which in fact marks Amphipods as having reached the destination if the initial state has any in the correct room and in the deepest position. Yeah, I think this will do it too. Basically, if my apod, if the home room positions for this apod contains the Amphipod's position and the home room is friendly. When I say friendly, that just means that all of the Amphipods in there are currently of the same type. That means you're not in that initial state where D is. We're just this sort of second condition here is just trying to account for this situation where you're in the correct room, but it's not friendly, right? So you're not in the deepest position that you could be. The other way I could do this is I could update get deepest home room position and just basically check if the state at that position does not equal this type. That's another way I could do this. But this is a case where we've just reached where we need to go. And so if it's in a hallway space, we'll do all this stuff. Otherwise, we're in a room space, right? And if we're already in a room space that we're supposed to be in, we'll just continue. We're not going to go carry forward. Otherwise, we need to be able to move into the hallway, right? Okay, and so what I also want to do here is I want to make sure that I'm matching the number of homeroom positions to what is appropriate for the input that I'm providing here. The input I currently have is the small one. So let's go ahead and remove some of these. In my implementation of the leftmost A move. So let's talk about the leftmost A, right? let's say we get to the leftmost A, and leftmost A's position will be down here, right? It's where it needs to be. And I'm assuming that's the one that you're talking about. Unless you're talking about my input here. Let's talk about the sample input, right? It will have some index, will come out of this iteration. It's not in a hallway space, so we'll ignore that. Let's get the homeroom positions for that A. So it's going to be like these two. Does it contain that position? Yes, it does. So we satisfy this one. And then it's saying, is it homeroom friendly? And it's not. So it will attempt to move. So this is actually incorrect. So maybe what we need to do is we need to have like this funny function, which is like, are you already where you need to be? Are you in the deepest position that you should be in? Which is basically like, yeah, I mean, I could just update this, right? I could update this, get deepest homeroom position. Or just get destination. Get intended position. And we're going to go over the homeroom positions that are ordered by deepest, that it's deepest to shallowest. And if the map of this destination does not equal some type, it's just returning a reference. Yeah, ampersand type. Okay, fine. If let some other equals map.get. So UberX, this is a really nice call out that you pointed out here. Destination. If the destination, if the other type. So if it's empty, let's actually do a match here. If it's none, we return some destination. If it's some other thing, we return it's some other thing. If other is not equal to my type, then we return some destination. Otherwise, we return nothing. UberX says this is the last bug that you had to fix in your implementation. So I think that's correct here too. Get intended position, and there's a path to the intended position. If apod so maybe I can just make the intended position out here. That's the state. And I need to pass in the type, so it's apod.type. If the intended position, if there is an intended position that's valid and there's a path there, we're going to add a potential move. We're going to add a move there. and then we're done. Otherwise, if you've already reached your position, maybe this should be the first thing, right? If let some intended position, some destination is equal to the intended position, if the destination equals apod.pos, then we are done. There's no additional moves to make, and that way we can get rid of this thing. Okay, there's a lot of code here. Sweet Jesus. Okay, we are running the simplistic thing, and we're going to run it again. Hopefully, it's not fast. I'm not sure what magic other people are using here, but I'm using a supposedly fast language, but I'm doing a depth first search just like the way everybody else is. It could be that I just have a bug here, but this is not proceeding particularly quickly. And that's also not the right answer, I don't think. 14,415. This is 14,481. So there's like some moves that are not possible given this new implementation that I should be making. All right, so the intended position here is like, let's get the homer positions. Let's assume they're sorted. Sorted from greatest depth to least depth, right? And I think that is basically true for all of these. 3, 5, 7, 9. This looks pretty good. We're going to get that intended position if, and the intended position, once again, let's take a look at the implementation. Let's get what is there in the map. If there's nothing already there, then we can move there. And then if there is... Okay, I think... just sort of think that this logic here. If the homeroom is friendly, then there must be... I think we can almost unwrap the intended position here because there's no way that the homeroom can be friendly and this be none. I almost like that as a kind of sanity check. If it crashes, that means we've introduced a bug. The other possibilities are just cost it could be that just our cost computation is not correct. Could be double counting something. What's the intended position again? It's always assumed to be the deepest. It's the deepest as long as the deepest is not, unless the deepest is already occupied by a friendly amphipod. So the intended position here is we're going to go through the homer positions that are sorted by depth. If there's something there, if there's nothing there at the deepest position possible, then we're going to return that. Otherwise, if something is there but it's not the type that we want it to be, we're going to also call it the intended position. What would be the intended position for leftmost A and the other A? So the intended position, oh, you know what? This is not working correctly because it starts in its intended position, but we're counting its own position. Yeah, okay. So there's like a base case problem here. In order to check the intended position, we need to actually pass its own. We need to just pass the amphipod entirely, right? If the destination equals the apod's own position, then we return the destination. Yeah. That's a great thing to point out. $57. Okay, so it's still not correct. That improved it and improved the runtime considerably. But it didn't get us perfectly to where we needed to be. So I'm going to say this. This is like nice progress. I've been at this for a number of hours in a row, and I need to get up and do some other things. But I'm going to pick it up later on this evening or tonight. I'm definitely earning day 25 of Advent of Code. Thanks to everybody who are in chat right now. If you're not subscribed to our channel but are interested in game development, Dom and I, Dom's not in the chat right now, but Dom and I, we do a stream once a week where we're working on video games together. Just in December, we're doing Advent of Code because I like to do it every year. But yeah, awesome, everybody. Thanks a lot, and I will pick this up in a couple hours. I just need to go and like eat lunch and stuff. I apologize for not getting to it because I feel like we're getting closer and closer. All right, take care, everybody.
5 minutes later.
Okie doke. After 4 or 5 hours of working on this problem, day 23, I'm back a few hours later after getting some dinner and some dessert, and we're going to take another crack at it. I am actually not streaming this live right now for a couple different reasons. One is that this problem took long enough that I started to get nervous, and I really wasn't sure whether I was going to be able to get it done in a reasonable amount of time, and for some reason just having a live audience made me feel weird. And the second was that I think while the live audience was actually really good, we actually had a lot of folks come in on stream. There was a couple people who I really appreciated being there, but I was kind of going off on a lot of different tangents and like sort of answering questions and talking about different programming subjects, and I felt like it was a little bit of a distraction to actually getting the puzzle solved, and I felt like I was kind of like just making the thing worse and worse. which is not to say that the suggestions weren't good. I was just like not able to digest the suggestions in a way that was effective. So we're gonna try to do this maybe in the comfort of silence, besides me talking, which I guess isn't really silence, but we'll see what happens if I just have a chorus of one going on my head. Anyways, we've tried a couple different things to solve this problem so far. One was to sort of improve upon Dijkstra's algorithm and make sure that when we look stuff up, we are not having to repeatedly hash a small-ish sized vector, but a non-trivial sized one over and over again. When we did some profiling in a flame graph, we noticed that it was just my program was taking a lot of time just performing hashes. That was one thing that we tried. Another thing that we tried was converting from Dijkstra's algorithm to just a simple depth first search. Under the suspicion that the cost difference between a lot of these different moves was so dramatic that maybe Dijkstra's algorithm just wasn't helping us. Now, that all being said, I managed to not only make my program slower, but also less correct. So I've kind of have to sort of resurrect my program from a shambles, basically, and see where I can take it. One positive thing, though, is that I think probably the big issue that I'm running into is that each time we are in a particular state and we're trying to find transitions to new states, the number of transitions that my program was coming up with was just too many. And so essentially the number of possibilities in the search was just proliferating too widely. And what I'd like to try to do is maybe take a hard look at the rules now that we've had a couple of hours away from the problem, and see if there's any kind of economies that I can take advantage of. So we're going to take a look. If I'm just looking at the puzzle prompt again, amphipods can move up, down, left, or right, so long as they're moving into an unoccupied space. So I think we have accounted for that. They take different energy, moving different steps. But there are some rules. An amphipod will never stop on the space immediately outside any room. That we accounted for, I think, pretty cleanly. Amphipods will never move from the hallway into a room unless that room is their destination room and that room contains no amphipods which do not also have that room as their own destination. So I was confused about this rule for a while. One of the people in chat on Twitch suggested that maybe I was reading this incorrectly, where the way that I read this initially was that I thought if an amphipod was starting in the wrong room, it could move into a different room that was also the wrong room because it wasn't moving from the hallway into that incorrect room. It was moving from another room into that room. But I think the reading that most people had was that you have to go through the hallway to get into that room. So what this rule really means is that the only time an amphipod can enter a room, period, regardless of where it's coming from, is through a hallway. It has to go through the hallway. The hallway is the medium for that. And so therefore, an amphipod can only ever enter a room if it's the destination room, or what I called the home room, right? Now, on top of this, one of the things that was discussed on chat before was that once an amphipod enters a room, and it can only enter the room if there's no foreign amphipods in that room, there's really no other point but for that but there's really no point for that amphipod to enter that room and hit any space other than the deepest one that it possibly can get into. And when I say deepest one, what that means is that if there's no other amphipods in that room, it should go into the very, very last space of the room. And if there are other amphipods in there, and they are all friendly ones, or the non-foreign ones, the ones that are supposed to be in that homeroom, you should go to the deepest one you can go to. Right. Okay. And then this last rule, once an amphipod stops moving in the hallway, it will stay in that spot until it can move into a room. And what this a room really means is it can only move into the room that it's supposed to go into. Because, like, basically, if you combine this third rule with this first one here. I'm actually not even sure why this third rule is necessary, right? Once an amphipod starts moving, and any other amphipods currently in the hallway are locked in place and will not move again until they can fully move into a room. This seems like it overdetermines this rule, right? Because if you stop in the hallway and you pay attention to the second rule, this third rule naturally falls out of it, to me at least. At any rate, let's try to chug forward. So what we've got here is a depth-first search version of this. Someone in chat said that their depth-first search version of the program ran in like 4 seconds or something like that. So it really should be pretty quick. I've got a lot of code here. I'm not sure how much of it is super necessary, but I'm going to sort of like, at least to myself, recite exactly how this works so I can recall. And in fact, I think what I'm going to do is I'm going to grab the sample, like the original sample output, and plug it into my program. So I can kind of analyze it and break it down into individual steps just to make sure that I'm writing, because I'm changing the algorithm so much, I no longer trust that the code that I write is at all correct anymore. So the new algorithm is just this thing called best cost. And what best cost is it's a recursive function. It takes our state. The representation of our state hasn't changed. It's a vector that contains a bunch of amphipods, and the amphipod really is just the type, and then also where that amphipod is currently on the map. Oops. Then the cost that it took to get to this state, and then a cache which maps basically a particular state to the best cost, or the cheapest cost that it took to get to this particular state. And then it says, okay, well, from this as a starting position, and this is a starting cost, what is the cheapest cost, given this baseline condition, that will get us to the finished state, right? And so our first condition, which is basically the base case for our recursion, is that if this state we can consider already finished, well, then the cost that we're passing in here is just, it can't possibly improve on top of this baseline, right? So we're done here. Otherwise, we need to actually now modify this state because we're not finished. We need to actually take some steps closer to a correct answer. And so therefore, we will do get next moves here. I think actually now that I'm saying this out loud, I was asking a question of why this particular rule is in place. Is this really, I think it's really there to enforce the idea that the amphipods are eventually going to settle into their rooms. You can't just iterate infinitely, right? Because if you normally do a depth first search in an open graph where backtracking is allowed, the depth first search is actually just never going to terminate, right? So that's why you need something like Dijkstra's algorithm, which is not really a tree search, or it's not a depth first search in a sort of recognizable sense, because it's doing some prioritization and sort of limiting the infinite recursion that would otherwise happen, the infinite iteration. Okay, so we need to evolve. Let's suppose that we're not at the end. We need to evolve this state so that it gets us closer to the end. And so what we're going to do is we're just going to say, so from this state, what are the legal moves that we can make? And this function is important. It's also, I think, in my opinion, the trickiest function to write in this whole program. This function is important because it controls our correctness almost completely, right? We have to make sure that this is correct. But it also, if we write it poorly, and I would posit that I did write it poorly, it also has the chance to basically create multiple iterations, many, many results could come from this function call. And many results that we don't even care about, right? So we want to make sure that this looks pretty good. So once we do that, what it's going to yield is essentially a potential move, which is just basically the ID or the index of one of the amphipods in our current state and the destination of where we want to move that amphipod. So we pull that amphipod out. we clone the current state, and then we update that amphipod's position to the new one. And then we do something interesting, which is that we sort this vector. And the reason why we sort this vector is that there are multiple amphipods with the same type. And we did a lot of analysis on this, and I'm still not 100% sure, but I think that this simulation doesn't really care about the history, and it doesn't really care that an amphipod with type A in position 1, it doesn't matter if that was the first amphipod of type A that arrived at position 1 or the second amphipod that arrived there. As long as all the types and the coordinates kind of line up, it doesn't matter how they got there. Right? So one way I kind of illustrated that before was I took something like this, and I changed the second instance of each letter to a lowercase. But as far as the simulation is concerned, I don't think it really cares. So maybe we should treat this state as basically the same thing if we, let's say, swapped uppercase A and lowercase a. What I'm saying is that these two states should be treated the same way in terms of our search. And so that's why we added this sort in here. This will make this kind of like order independent. And then what we will do is we will basically we'll look into our cache to see, hey, have we gotten to this state before? And if so, how much did it cost us to get there? And then we'll calculate the cost of how much it took to make this move based on our current cost and however much energy this amphipod takes. That's why we have a Manhattan distance and a step cost for each of these amphipods. In fact, I'm going to just call this function Manhattan. Mandist is really weird to me. Now, if this move's cost is greater than or equal to the previous cost, or if the previous cost is less than or equal to the next cost, so if the cost that we got from the cache is actually cheaper than whatever we just calculated, then we don't really care about what we just did here. We need to just like get on with our lives and go to the next thing. Otherwise, we're on to something new. We have a new thing that gives us progress. So we're going to write this into our cache. And then we are going to make our recursive call here. We're going to make our recursive call with the next state with the new cost, pass the cache in there. And then we're going to see if this particular recursive call produces something that's better than our current best. Right? And our current best right now is just like a really huge number. It's the biggest possible score that we could get. And once we do that, we'll return, and we basically just cross our fingers and hope that the recursion works. Now, when I was running this, I was basically running into either issues where I would blow out the stack, and that's what happens in recursion if it just runs too long, right? And there are ways of getting along that, but for the purposes of advent of code, if you're blowing out your stack for recursion, you've just done it wrong, right? So that was one problem I was running into. The other problem I was running into is I just wasn't getting the right answer out of it. So we have got the sample input in here, and we should get an answer of 12,521. And if I run this right now, I believe this is day 23C, I get 12,599, which is like slightly more than what we should be getting. And I think what that means is we are not getting all possible moves from this get next moves function. Or we somehow have a weird bug in here. In any case, let's go ahead and just like investigate this a little bit and see if we can come up with the answer. So this is a surprisingly subtle function here, get next moves. It's really tricky because the rules of this are kind of tricky. So what we're going to do basically is we're going to take a particular state that we start with, and we're going to basically yield a vector of this weird tuple here. The tuple is basically indicating, okay, which of the amphipods in this vector do I want to move? And where am I going to move it to? And we have to basically apply all the rules of the game here. And then also be a little bit clever and maybe eliminate some moves that are technically correct, but then ones that like don't actually help us get to where we want to go, right? Now I made this variable called state here, and I actually think maybe I should just call it the map. I'm going to call it the map. It's not just a cute name because it is a hash map, but it's actually like a map of our current state, right? That's maybe a better way of calling it. And what I'm doing is I'm going over this vector for amphipods, and I'm kind of reversing the mapping here. This maps, I guess, amphipod IDs to their type and their position. I want something where I can basically pass a position into this data structure and get either the amphipod or its type out of that, right? And that's just what I'm doing here when I build this map. So I'm going to iterate over all of my amphipods, and I'm going to get something for each amphipod called its intended position. And this is a subtle function here, right? We're passing in the amphipod, and we're passing in the current state of the map. And the intended position of the amphipod is basically A, what room do they belong in? And B, what is the deepest possible position they can achieve in that room, right? And this needs to account for all kinds of weird situations. So what we're going to do is we're going to get all the homeroom positions for this amphipod, okay? When I say homeroom positions, what I'm just saying is, if the amphipod is A, then it's just this position and this position. And the amphipod, if it's amphipod B, then the homeroom positions are these two cells. If it's C, it's these two. And if it's D, it's these two. In fact, I can even just go to this function and eyeball it, right? So if it's amber, that's type A, then it's just like, are you in the third row, third column, or the second row, third column? And then so on and so forth, right? In the part 2 version of this, the graph is a bit more complicated. The homerooms are deeper, and you have to have more. I added this comment up here saying that it must be sorted from greatest depth to least depth. In other words, the rows need to be higher earlier in this vector. And this matters because of the way that I implemented this intended position function. So we're going from the deepest homeroom positions to the shallowest ones. And if the deepest position for this amphipod is the amphipod's position, then we're done, right? The amphipod is already where it's supposed to be. Otherwise, we're going to basically look at our map and say, okay, well, the current homeroom position that we're looking at, which is deep, we're going to look at what's already there. Okay, and that's why we have that map. And if there's nothing there, then this is the deepest position that this amphipod should try to get to, right? Otherwise, if there is something there, then the only reason why this amphipod shouldn't try to get to that position eventually is if one of its friends, so something with the same type, is already there. However, if there's something there, but it's not of the same type, that thing is foreign and is eventually going to get out of there. So this amphipod should eventually try to achieve that position. So that's what this is saying. If the other thing's type is not the same as my type, this other thing is foreign. It's not sitting in the right room. So what I'm going to do, so basically this amphipod says, well, I should be in that spot, so that's where I'm going to go, right? So actually the only time we get past this, the only time we go beyond the first iteration of this function, if you think about it, is if other's type is actually equal to the amphipod's type, which means that there's somebody else there where there should be, and so therefore we should just continue, right? Here's a question. Will we ever get to none, right? Do we ever get to this point where we have nothing getting returned? And I think the answer is no, right? There should always be some intended position because it doesn't even matter if it's occupied or not. So I'm actually going to change this function and make it something where we always get something concrete. Okay, so that's actually a decent improvement here. And I'm just going to call this unreachable down here. And let's go ahead and get rid of these sums. The sum here is just referring to, it's just the way that we return option types in these functions. All right, so we expect to get somewhere in this iteration. Okay. So the intended position, once we get that, we can say if the intended position is equal to the amphipod's current position, we're done. This is where the amphipod's just supposed to be. This is its destiny. Okay, so otherwise, if the amphipod is in a hallway space, okay, all it can really do is move towards its intended position. And the only time it can actually move to its intended position is if the homeroom for that amphipod is what I call friendly. And what I mean by friendly is that it's occupied by only amphipods that are supposed to be there. And so what I do here is I grab the homeroom positions. That's the function I used before. And for each of those, or for all of them, I check to see what's occupying that spot. If it's nothing, that's fine. And then if there is something there, the type of that amphipod sitting there needs to match the type of the homeroom. So that makes some amount of sense. The intended position is no longer an option, so I can just put this as the intended position. So what I wrote here is that if there is a path from this hallway position to the intended position, we're just going to go ahead and make that move. Otherwise, we can't make that move, and there's nothing for us to do, so we're just going to keep going. Finally, in this case, we're not in a hallway space, and I'm already seeing an opportunity for a little bit of optimization, and I thought of this while I was eating dinner, but basically what we're seeing here is that we can, if we're not in a hallway space, what this means is that we're in a room space, but not in the intended position, right? And in fact, we're probably in a different room than we're supposed to be. So what we can do is move into a hallway space. This isn't actually technically the only thing we can do for our turn, and I'll get to that in a second. Let's just pretend that all you can do is move into hallway spaces. So we're just going to go over every single possible hallway space, and if the hallway space is already where the amphipod is, which I actually don't think is possible, right? Like this condition here is this little bit of sloppy coding, right? Because we already said if the amphipod is in a hallway space, then it's only going to run inside this if block here. There's a continue here that will prevent execution from getting down to this point, which means that if we iterate through all the hallway spaces here, this will always be false. So I'm getting rid of this. So if there's no path between where the amphipod currently is and this hallway spot, then we're just going to keep going. Otherwise, we actually consider this to be an option for where it can go. So I said I wasn't 100% happy with this because actually, if we're in the wrong room, there is one condition that would actually simplify all of this, which is that if there is a path directly to our intended position, then we should just go there directly. And the reason why I didn't add that into this originally was that this hasPath function only works if you move in one direction, both on the x-axis and the y-axis. And in particular, in only one direction in terms of rows. But if you look at the way that these are structured, if you're in the wrong room and you want to go to the right room, you actually have to go up on the y-axis, over some amount, and then down on the y-axis again. And for basically reasons of laziness, I didn't want to write a function that did something that sophisticated. Now, that being said, I think we can actually do this relatively trivially, in the sense that if we know that the hallway, the geography of this of this sort of program is really, really limited. We know that the hallway is at row 1, right? So we could know that if the row value for the source and the row value for the destination are both greater than they are both greater than 1, then we can actually just combine this. This has path can be a little bit recursive. Well, it already is recursive, right? It's recursive here. We can just say, well, if this destination is basically in a room and this destination is in a room, we can just actually break this up into two paths. Do you have a path to get out of the room into the hallway? And then do you have a path to go from the hallway into your destination, right? So that's something we can definitely do, which means that we should probably check to see, where are we calling has path? We should probably check to see in our get next moves, really here, if you're already at your intended position, you should just go. Otherwise, if there is a path to your intended position, you should just go again, right? And it doesn't matter if you're in a hallway space or not, right? If there's a path directly to your intended position, then you should just continue. So let's try to do that. So one thing we can say is if source.0, so the row of this, is greater than 1, and destination.0 is greater than 1, then we need to go up, over, and then down. Room to room transition path. What this really is we want to return has path of source, and then we're just going to go to the hallway outside of this room. So we're going to do source, we're going to do row 1, source.1, which is the column for source. Do you have a path to get out of this room? And do you have a path to get from 1 source.1 to the destination? And that's it. And I need to pass occupied in there as well. So this should just be fine going from room to room, right? It's just breaking the path into two components, and we'll just see if the path is open. It's the same logic otherwise. Okay, so now what does that allow us to do? What we can say is, like, if you're already at your intended position, then you're done. If has path from apod.pos to the intended position, then the only thing we should do is move to that intended position. That's what our rules are basically telling us, right? So we can do res.push I intended pos, and we continue. And now, if we are in a hallway space, we actually can't, if we can't move to our intended position, then we're actually done. We can't do anything from here. Oh, I need to pass occupied into, I think this is and map. So if we're in a hallway space, but we can't move to our intended position, that means we're stuck. We're basically in this rule right here. If we're stopped in a hallway and we can't move into a room that we're supposed to go into, then we're done. We don't have any options right now. Otherwise, we are in a room space and we can't go to our intended position, and all we can do is move into the hallway space. Apod is in the incorrect room, can't move to its intended room, and therefore can only move into the hallway. Okay, so that's maybe a little bit better way of handling this. Homebrew is friendly. Aren't we calling this transitively somewhere? Oops. No, it doesn't look like we're calling it at all. I don't remember where I got rid of it. That's how short my memory is. I feel like we just talked about it. But let me try running the program now. Did I change anything? Well, now it takes longer. So I think I might have broken it. What's interesting is if this isn't an infinite loop, then, well, if this isn't a Stack Overflow, then we're infinite looping in an interesting way. I'm just running it one more time. Sometimes I've had issues with compiling this where I will compile it, but it seems to be running the old executable. I think it might just be a timestamp thing. And it's a timestamp thing because what I'm doing to create these new directories is copying the previous one, and it also includes the build artifacts from the previous one. Maybe I should write a little script that will remove the target folder so I get a fresh compile every time. Okay, so I think maybe the modification I just made is sort of throwing a wrench in the works a little bit. Perhaps then we can actually just try to debug what each of these next moves look like. So we're going to print our current state. We're going to add an extra new line at the end here, and then we're going to put the cost. And then here, we're also going to print the resulting state. Going to call this a next move, possible next move. And what we're going to do is let's do a clone of the current state. And then we're going to apply a move. Actually, I think apply will do the cloning. So we'll do the current state. We'll do ID next position, which is our next move. And we will print the state here. And then we will print a new line here. Apply move. I think we need to just stick an ampersand here. Okay, and then I think what I'm going to try to do is just, I want to only do this once the first time. I don't know if I can because the recursion happens here. Okay, so this is interesting. We basically hit an infinite loop almost right away. So maybe it's a has path issue. Possible next move is just moving the just moving this thing up into the corner, which actually seems like the right first move. It can't move into any of its intended positions. All it can do is move into the hallway, so it'll just move into the first hallway position here. Then we're trying to find the best cost for it. Oh, and the way that I'm rendering this actually makes me think. Why is there an extra space down here? Is occupiable space. Is hallway space. Aha, is room space. Maybe what I should be doing is trying to make some constants here, so this is a little bit less crazy to think about. Const. Let's call it room height, which is a U size, and it currently is just 2, right? Our room size is just 2. And maybe there's a way that we can apply that such that this is a little bit less flaky. The first room row is 2. Does it need a type? What's your malfunction here? Value of type vec i32 i32 cannot build an iterator over type usize integer. Oh, is it just because these are U sizes? What if my room height was just an i32? Then it has no problem. Okay. Those are all the hallway spaces. I agree. It is a hallway space if we're in row 1, and it goes from column 1 to column 11. That's fine. And it's a room space if the row so if the row is less than 2, or 2 plus the room height is less than or equal to the position 0. So I think if I want to use less than equals on both sides of the or sign here. So if you're in the first row or above, you're not in a room. Now, if you're at 2 plus the room height, you're actually in the first row outside of the last room row. You're also outside of a room. We're returning false here. And then we get a 3, 5, 7, and 9, which is just basically the columns that we can be in. All right, that seems a little bit more sane to deal with. Okay, so this is printing better. I fixed that bug. It's not going to fix our infinite loop, though. So where are we infinite looping? Finding best cost. So we're getting here, and we're going here, and then once we get to this point, we don't even get into this, because get next moves for this state is iterating infinitely. So that is what it is the second time we get into get next moves. So why don't we try to debug this? Did I mean day 23C? I did. Okay, so I need to adjust my launch.json. And I really need to make it so that this is a little bit more flexible. Day 23C, let's try it. Okay, so this is the first time we get in there, and I think this should be okay. This is the second time we get in there. Now we're going to get the intended position for our amber amphipod. That's this one here. Now, what's its best move? What's its intended position? So its intended position should be where it currently is. 2, 3. It is at 3, 3. So why is this intended position 2, 3? That's an interesting thing we should try to figure out. So the first time around we don't care, and then we're going to step in here, and now we're going to step in to get intended position. This destination is 2, 3. Ah, interesting. I think I reversed the ordering of this. Can I reverse this iteration? Rev? Yeah. So I'm going to try running it again. All right, so what's our infinite loop this time around? Should be I think a similar place. So it's interesting to me that so the intended position now is 3, 3. So that's fine. I'd like to know which amphipod is actually infinite looping. So which one are we currently on? I is 1. So this is the other amber one. So that's this one. Oh, that's right, because I sorted it. Its position is 3. Row 2, row 3, 9. Okay, that's correct. And it should not be able to move anywhere, right? So it has no path to get to its intended position. That's true. It's not a hallway space. And it basically should have no ability to get into any hallway space. And so what we should be doing is we should be iterating to the next thing, which is good. Okay, now we go to the bronze one, and this bronze apod is at 2, 3. I wish I knew how far along we were. So I think we're in the first iteration still, because row 2, column 3 is this one. So we haven't moved anywhere yet. I think maybe I needed to do another skip ahead. Yeah. All right, so we've got our amber amphipod. Why don't I just print the ones that were, why not? Let's eliminate the guesswork out of this. So it's the bronze one at 1-1. Okay. That's helpful. So we're going to go amber, amber. Going to set a breakpoint up here, and we're going to advance to it. Now we're getting to the one that's going to infinite loop. Okay, the bronze one at 1-1 is the one that just moved. Right. So it's this guy right there. And we're going to be asking the question, does it have a path to get to its intended position? Which is 3-5. And we infinite loop there. Okay, so that's great. It's great because we can reproduce this pretty easily. Go to the next one. We're going to go here. The amber, amber, amber. Did I go too early? I think I might have gone too early. No. Amber, amber. This really should be. Did we have 3 ambers? What? Why did that happen? Let's take a look at our state. Amber, amber, bronze. Bronze, copper, copper. We're at amber again. Now we're at bronze. Weird. Okay, so I think this is the one where get intended position is not succeeding. We're going to dive in. Destination is 3-5. Actually, this already worked. So now it's has path. We're going from 1-1 to 3-5. This is not a room-to-room path. And then we get our delta on the y-axis. We're going to move in the direction of the y-axis. And if it's an occupiable space, so is it actually a space on the map? And 2-1, I believe, is a space on the map, right? It's a row to column 1. No, wait, row 2, column 1 is not occupiable. This is it attempting to go down. Okay, so that's good. So if our delta is not 0, the S indeed will go. So it should be basically us stepping to the right. So this is this guy moving 1 over. So we dive in. Now we're at 1, 2, and we're trying to get to 3, 5. I think I see what the issue is. This whole navigation is going to basically try to get a path, and I will try to expand this for you, for everybody. It's trying to get a path, always looking downwards first and then moving over by 1. So it's going to dive down here and not find 1. If we keep going, yeah, this is what I expect, and we dive into this, and we keep going, now we can actually move on. Now we can actually move on the y-axis. And we go in. Now we're at 2, 3. And now it's a room-to-room transition. Right, so this is the case that's causing it. It's trying to do a room-to-room transition from here to the destination. So why is that infinite looping, is the question. Oh, I see what's happening. We are just going up and then down, and then up and then down, and then up and then down, and then up and then down. So I think we need to be a little bit smarter about our strategy here, and we need to account for the fact that we're in the hallway. Let's do a hallway to hallway path. So if we're just in the hallway, all we need to do is iterate over source.1 plus 1 to everything including destination dot 1. That's the column. So for blah in this, actually what we want to do is call this the call. And then if occupied contains key one, because we're in the hallway, And then the column, then we return false. So either it's a room-to-room path, or it's a hallway-to-hallway path. Or it's a hallway-to-room path, and then finally our last option would be a room-to-hallway path, right? So for a hallway-to-room path, what we want is return has path from source to 1 and in the destination column, and we have a path from the destination from 1 destination column to the destination. And we need to return occupied. We need to pass occupied as well. Finally, we have a room to hallway path. And so we have to go upwards first. So we're going to, this is just going to be has path from source to the hallway, which is 1, destination dot, and then source dot 1, pass occupied. So we're basically going upwards from the room into the hallway. We're going to go up. We're going to stay in the same column. And we have a path from 1 source 1, which is where that previous one was, to the destination. And I just realized we have another bug. And the bug is a hallway-to-hallway path. We're assuming that we're counting upwards. But what we really want to do is we want to approach the hallway because we can go to the left as well, right? So what's the best way of doing that? Well, we can just do let call equals we can just say let A B equals, or let's call it the left and the right is equal the, is there a min-max such thing? Let's say destination.1.min. Destination.1 let's think about this. We want to approach dest from source. So we can just say let dj equals dest.1 minus source.1. That's our delta. And what we really want is just the sign of that, or whether it's -1 or +1. That's signum. And then we can say let mute call is equal to source dot 1 plus dj, and then while dj is greater than, while call does not equal the destination, which is dest.1, we will check to see if occupied.contains key of the hallway row, which is 1, and the column that we're currently on. And if it is occupied, we'll return false. And then we'll do this again. Call equals plus equals DJ. So let's do a hallway to hallway path example going from the left to the right. Let's say we're in column 1 and we're going to column 2, right? So we're going from 2 to 1. 2 minus 1 is 0. Oh, sorry, 2 minus 1 is 1, obviously. Then our column that we're going to is going to be 2 minus 1, which is 1. While they're not equal, they are equal actually, right? So we would actually come down to here, which is return true. So I don't think this is actually satisfactory just in the case that we're only moving one space, because we actually need to check for the occupied spot right here. So maybe what we can do is we can do the column plus DJ right here. And so this is just going to equal the source column. The source column. Okay, so if we're going from 1 to 2, this is going to be DJ is going to be plus 1. 1 is not going to equal 2. We're going to add 1 and 1, which is 2. We're going to check to see if that's occupied, and if it is, we return false. Otherwise, we break out and return true. Okay, let's go the opposite direction, going from 2 to 1. Okay, so call is going to start off at 2. DJ is going to be 1 minus 2, which is negative 1. And while 2 does not equal 1, which is true, we're going to subtract 1 from 2, which is 1. We're going to check the spot 1, 1. If it's occupied, we'll return false. Otherwise, we'll return true. So I think this is correct. Okay, and now we're getting a stack overflow. So we overflowed the stack almost immediately. So I think we're still overflowing the stack in has path. This ended up being the most complicated thing. This is crazy. For the amber amphipod. All right, that's fine. That's fine. Let's debug. Okay, we already infinite looped. So let's try this one more time. It's the one at 3.9 that's having an issue, right? I think I'm hitting this macro 3 times because the println macro actually expands to something quite a bit, like many more lines. I think that's what's happening. So I think getting the intended position, that code is fine. It's this has path that's kind of screwing me over here. Do I have a path to 2.3? So this is a room-to-room path, and that is correct. So we want to try to go from its current position to the hallway position right outside of it, outside of that room. So let's just dive into that. And this should already just fail, right? It's not a hallway to hallway path. It's a hallway to room path. This is a room to hallway path. So we're going to go, do you have a path from the current position to the position outside the room? And didn't we already call this? I think we already did. I think this is the source of our infinite recursion. Yeah, so we have a room to hallway path, and this is just basically calling itself over and over again. So maybe I want to break this up into something like this. Has path vertical and has path horizontal. Don't love it, but that's what we're going to do. The horizontal one is like this. And we're going to do source column, which is an I32, and the destination column, which is an I32. Or rather, it's the row. This is a vertical path. And actually, I think I'd already written the horizontal version, so let's actually write that one. Has path horizontal. Source column, I32. Destination column, I32. Returns a bool, and we need to pass in the current map. Okay, so the row, the current row is where we are, is the source column. The change in row, which is DI, is the destination column minus the source column. And while the row does not equal the destination column, we add or subtract 1 from the current row, and we check to see if it's occupied. So we need to actually know what oh, this is row. I had all the letters corrected originally. We need to know what row we're on, so that's got to be provided. Guess it's always going to be 1 because you can only move horizontally on row 1, but you know what? That's okay. So this is, do you have a path moving horizontally? You start at the source column, you get the increment here. Let's just call this the inc. While you're not equal to your destination, we increment, is the current spot occupied? If so, we return false. Otherwise, we return true once we're done. So the vertical version of this should be structurally very similar. Anytime we're seeing the word call, we should just basically replace with row. And I think that's it. We have a source row. We're going from the source to the destination. So this is our direction of subtraction. We get an increment. While the current row is not equal to the destination, we increment the current position, and then we see if the current position is occupied. If so, we return false. Otherwise, return true. Okay, so I think that's what we want to do here. So now I think we can kind of maybe change the logic of this a little bit. So if it's a room-to-room path, what we want to do is we want to say, do you have a path? Do you have a vertical path? From source.0 to 1 on the same column that the source is on? And do you have a horizontal path from the source column to the destination column in row 1. And do you have a path, a vertical path, from the hallway row to the destination row in the destination column? Okay, that's horrible. A hallway to hallway path is just the horizontal. Source column, destination column, the row is 1. And then the hallway to room path has path horizontal from the source column to the destination column in row 1. And you have a vertical path from the hallway row, which is row 1, to the destination row in the destination row is actually 0 into the destination column. This is one area where I wish I wasn't using tuples because it's really hard to think about the 1s and 0s. Finally, we have a room to hallway path, so this is just I think it's just this piece. Room to hallway actually is a vertical one first. That's this. So you want to go vertically from the source row up to the hallway row in the source column. And then you want to go horizontal from the source column to the destination column. On the hallway row. Gosh, that's complicated. And then this should look identical to this. Is that right? Source 1, dest 1, 1 occupied, 1, dest 0, dest 1. And this should look like this middle thing. Yep. Okay, so at least we did this a bunch of times and we have a certain amount of symmetry to it. Let's see if this just runs. Okay, that's running. I want to maybe eliminate my prints to see if this will actually terminate. Adding the IO here is obviously going to make it much slower. $8,397. So somehow we made some moves. Somehow we made some moves that were not possible. And I think the reason why is that we're doing Manhattan distance when this room-to-room path is actually not just Manhattan distance. So if it's a room-to-room path, then we want to return Manhattan of source to the hallway plus Manhattan of the hallway to the destination. Otherwise, we just return Manhattan. And where else are we calling Manhattan? We are calling it down here. And so we want to get distance. 12,541. We are 20 over. So we're missing a potential move, or we have some weird math in here. Ugh. I feel myself getting closer, but this is such a finicky simulation. I suppose I could try to return the path that it's trying to send me down. And that might be a way to see if we are doing a move that is less efficient than it should be. So in depth first search, I believe we just need to accumulate this, right? So what we can do is, let's go to best cost. And maybe what we're going to do is we're going to return a tuple of what moves. And a move is a U size I32, I32. Gosh. That is a tricky bastard. It's actually going to be a vector of these things, isn't it? So we're going to return cost with an empty vector. If we're finished. Otherwise, we got to do something a little bit tricky here. So we can do best score here. Let mute best path equals an empty vector. We're not even going to use it. And then we're going to say if cost is less than best, then best equals cost, best path equals path. And then we're going to return best and best path. And I think this path needs to actually prepend something, right? We need to actually, is there a prepend, pre-push? We'll just append the current move that we're on. And the current move is ID next position. I really want to just like prepend. Really, guys? This is the best I can do. Let's make path mutable. What I can do is reverse this once we get this. We're calling best cost down here. Let's take a look at what this is. We're going to reverse the path, and then what we really want to, we can print the cost. But now we actually want to print the changes in state. So we can say for step in path, we are going to apply the step. We're going to print the state. I'd like to add a new line here. And then continue. Sweet. Okay, so what are the moves that are actually recommended? First move is already incorrect. Tricky. Moves over here. This moves over here. This one moves back to where it was, which seems pointless. This is actually, this step is already one that should be illegal. Wait, do I even understand what's going on here? It seems like the two things are moving at once, which doesn't seem possible. Did I print it out correctly? Is the sorting throwing me off? Maybe I need to sort this state after every move. Okay, that seems like a little bit more sensible. Okay, it moves to the side. This one moves to the side. D moves to the side. A moves out. Then this D moves out. Then the B moves to where it should be. The D moves where it should be. The second D moves where it should be. B goes to where it should be. B goes where it should be. Okay, so we were actually successfully able to solve the puzzle. For whatever reason, we weren't able to... I want to know if this path is ever tried. And if not, why? What if I got rid of the sorting? Because that doesn't matter. Same thing. Gonna slim down some of these variable names because it's not super useful for me to. It's a little bit easier to read if I can just slim some of this stuff down. That was my bug. I was passing in the wrong cost there. Too many variables. Okay. I'll take it. Now let's try our legit input. $14,415. That is looking correct to me. And so let's take their giant input. Getting rid of that. Okay, we gotta tab this back over. And then we need to adjust the room height because that's hard-coded. The room height is up here. That is 4 rows high. We're gonna run it. Takes a little longer. Still spits out an answer. 44,169. Okay, so that's correct. I wonder if sorting it, I'm going to add those sorts back in there. Is that going to be a little bit faster? It did seem quite a bit faster. Okay, well, let's get my puzzle input. Let's get the legit thing. We'll paste it in here, but it does need to be modified because we need to add this middle section in there. Go ahead and run it. Runs nice and fast. I should probably get rid of this printing. And we will go ahead and plug it in. And we got the right answer. Wow. So I think I had the right intuition the entire time. I mean, we did have like Dijkstra's algorithm in there, but I don't think Dijkstra was the problem. It turns out, I guess the search space is small enough that really Dijkstra's algorithm doesn't matter. And they also gave us some rules that really made depth first search, I think, a lot more viable to use. The the thing that I got tripped up on is basically the complexity of the rules, really. And it really did help the speed of this program for me to really think about next moves and kind of slim down the moves that we could actually achieve. And in particular, always trying to move the intended position if we can. I think that removes a lot of the complexity. Great. Well, that was, I think, by far the most time-consuming problem of this year's Advent of Code. Probably not all time for me, though. There have been some that were really, really tricky. But potentially, this is going to be the trickiest one of the bunch. That being said, we have about 1.5 more puzzles. Usually this part 2 of day 25 is not a real puzzle. Usually like click a button. So we still have, I guess, tomorrow's problem, which actually got released an hour ago. And then we have the Christmas Day problem. I think for now I'm going to clean this up, commit it, and then we'll try to tackle tomorrow's problem properly tomorrow. All right. Take it easy.